Well, thank you very much, everybody, for coming to this lecture this afternoon. Yes, so it was a very comprehensive introduction, but if I had to define in one sentence what we do, basically we carry out research projects in the field of uncertainty quantification, mostly for engineering problems, but not only in practice. We have also some exotic applications, and as Ryan said, with different keywords or topics from reliability, sensitivity analysis, model calibration, optimization under uncertainty. And the missing word is basically surrogate modeling. We also developed quite much these techniques now for more than 2 decades. So today, along with these lines here in different research topics, I will, as it was said, mainly focus on surrogate modeling with first longer lecture on polynomial chaos expansions. This first lecture probably will be 2 hours, so we'll manage the break somewhere probably in the middle. And then one on Gaussian process, which is also known as kriging. And I will show some application of this also to global sensitivity analysis because it's very much connected. Okay, so in computational sciences in general, we nowadays use computer models, which I also call simulators, to basically represent complex engineering or natural systems. In geophysics, I would say it's more natural systems, for all kinds of purposes. And these models, basically, that we use, we are not basically doing data science or machine learning. We do physics in the very first sense. So those models basically are first defined by mathematical equations that really describes the physics. So typically mechanics, electromagnetism, fluid dynamics, reaction chemistry, and so on and so forth. And as you know, in most cases, those equations are partial differential equations. So when we want to then really solve these equations for real problems, complex geometries, complex boundary conditions, basically we have no closed form solution. So we use discretization techniques, typically finite element analysis, finite elements, finite volumes, finite differences maybe sometimes, at least in time domain, to basically transform these continuous equations into discrete ones that boil down to some kind of linear algebra problems. And then that's where computers are very efficient to solve large-scale such linear problems. And then, yeah, as I said, not everything is linear, so sometimes it's a bit more complex. We have algorithms that can solve these discretized equations. And so if all this is put together and works, then we can use the computational model basically first of all to explore what happens if we vary input parameters of the model. So that's what I call in engineering applications virtual prototypes, because it's like changing the design of a system by changing parameters. But generally speaking, is exploring the space of input parameters and see how varying the inputs changes the quantities you are interested in with your model. If you have done this already, then next step can be to optimize the system. So if now you use a model to compute certain performance criteria in a very general sense for your system, usually you want to optimize this, maximize performance, maximize energy production, for instance, under certain constraints that makes this feasible. So again, this is kind of putting an optimization loop, could be also multi-criterion sometimes, on top of the model itself. When it comes to assessing the robustness of the model and its predictivity, you usually have also to address the uncertainties, because in most cases, you don't know exactly, even if the model, the physics is well described, the discretization of the equation is well done, state of the art and everything, you not necessarily know exactly what parameters you should use so that model represents the reality you want to model. And then that is possibly more related to engineering applications. What we call reliability is basically explore extreme scenarios where the system would fail compared to this usual or nominal behavior, and typically compute a probability that the system does not fulfill certain requirements. And finally, all this usually works if you have the full loop by comparing or assessing your model predictivity with experimental data, field data. And this means that you have to use some kind of calibration techniques. Okay, so all these things can be put in a probabilistic framework, in the framework of uncertainty quantification. And it's very general purpose. So from now on, probably you know, at least from the presentation, that I'm not a geophysicist. But what we will present today is really very broadly applicable, because what I will call a computational model is really nothing but a kind of a black box, which happens to be blue here, but that has a number of input parameters that you have clearly identified. Could be a huge number, could be like also here time series, a field, or something complex, or at least high dimensional, and that produce certain quantities of interest starting from a few scalar, let's say, again, performance indicator or aggregated quantities, but it can be also time series or even output fields, okay? For sure, what I mean here is that as long as you have defined what are exactly your possibly long list of inputs, if you run the model many times with the same inputs, you get the same outputs, okay? So, but what's happening in between with the computer code maybe has been done by others, by colleagues, by specialists of other fields. So we are basically only playing with the input and the output, so you can really see this as a map from the inputs to the output. A map that, unfortunately, we don't know analytically, but each time we query the model, we put some input parameters, we get the outputs with certain computational costs. So in practice, for realistic models, can be hours to get a single run carried out, but in principle, you can do this for as many x's as you want. Okay, so in my field, so basically computational mechanics for engineering applications, typically realistic models are finite element models. The parameters describe the geometry, the loading onto the system, the material properties, especially when it's non-linear constitutive laws, different parameters. And what we predict is typically displacement, stresses, strains, temperature if it's a coupled problem. Could be flow if it's also coupled with some kind of porous media, for instance. And in between, again, the model can be very simple to very complex. So today in applications, I will mostly show very simple applications with analytical equations, just for the sake of showing also reference solution in that case. But again, it can be a very complex, costly finite element model. It can be a chain of different models, some models that maybe, I don't know, homogenize some microstructure, and then some macroscopic model, and then some post-processing, for instance. So just keep in mind, basically, a model has x's and y is m of x, and that's it, what we need to understand or to have in mind. Anything that can be put in this format works, basically. Okay, so then that would be great if then we completely master the x's to put into the model to get the predictions. But as I said, in most cases, it's not possible. Again, talking with some kind of engineering or design language, we use computers to design systems, like here it's a part of a car, or beams here for civil engineering applications. And there are always differences between what you design in a computer and then what you finally build. For the cars, typically, if you design this and optimize this in the computer and then produce 1 million cars, they will all be different, this subsystem, because in between you have different manufacturing processes, different tiny difference in the dimensions, in the material of metal sheets, for instance, if it's here mostly steel. And you can have also variability in the properties. So for steel, it's quite stable, but if you do concrete applications here, concrete basically is made locally with the local ingredients in most cases, aggregates, sands, and gravel, and so on. So you can have really big variability. Okay, so you have to account this in some sense. And when you talk about big systems now, typically infrastructure, building bridges and stuff like that, the load applied onto this can also be very uncertain, because then you have to account for natural hazards, so typically earthquakes or flood or whatever climate extreme loads, snowstorm. I heard that tomorrow there will be a snow storm on Hagen. Well, let's see. Hurricanes with big winds and so on. So these things, this kind of event we basically know from recording. We also have short-term predictions for weather forecast, for instance, like tomorrow. But yeah, at the scale of such infrastructure here in the next 50 years, you cannot predict nowadays what will be the highest wind and stuff like that. And even disregarding climate change. So there could be extrapolation, but this is very uncertain. So all this, again, if you want to model in a reasonable way, you have to admit that you don't know perfectly and then represent this in the proper way. And that's where it comes now to this framework to put together all these complex computational model and uncertainties. Basically, there is like widely accepted scheme that I present here, that you start from the model, as I explained before. That has to be solved, of course, beforehand. So you should work with something that is somehow predictive from the reality you want to represent. And basically, this has inputs and outputs. That's what we remember. Oops, sorry. Now, the second step for this uncertainty quantification framework is to look at the information or the data you have on all the input parameters of your model and see how much you know it, if there's some kind of variability, if there are things that you know perfectly and so on, and represent this in a probabilistic way. So basically, each parameter, instead of being now a number, will become a random variable with a given distribution that you have to decide. And this, of course, is not part of the talk today. Depends on the amount of information you have. So in very, let's say, pre-design phase for engineering application, or in cases where you address a new problem with very little knowledge, typically parameters will be just represented by bounds, like lower and upper bound, which is realistic, physically feasible, and maybe you don't know more than that. So that will be the first starting point. Later on, if you have much more data accumulated, then, for instance, you can do a real statistical inference and really fit the best distribution that represents the variability of your observed data. But in the end, for sure, you will end up with some kind of probabilistic modeling. Here also, you should not disregard a possible correlation or dependence between parameters. So sometimes you cannot consider that all the parameters of the problem are completely statistically independent, but there are also methods to handle this. So once you have these two ingredients clearly defined, then we do what we call uncertainty propagation. So then, if you imagine here just one quantity of interest, here that should represent a geotechnical problem, and here you just have some soil and then an excavation. So let's say that the output is the critical height of the excavation that you could get without any other support before it collapses. So one single quantity. Then now it becomes, as it's a function of the inputs and the inputs are random, now it becomes also a random variable. So you want to characterize the statistics of this output quantity. And of course, sometimes there are not just one output, but many, or even time series of outputs, or even more complex things. So characterizing the statistics means trying to find out maybe the distribution of the output, but as summarizing parameters, maybe just the mean and variance and certain quantiles, or in certain cases, the extreme values of the distributions. That's what we call this so-called probability of failure. Another very important topic in this framework is what we call sensitivity analysis. So this is also quite easy to intuitively understand. If you have a model that depends on many parameters, each of them with certain uncertainty, what happens in practice is that your output of interest here usually only depends on a few of these inputs. They don't play all of them. If you have 20, 50 parameters, they don't play an equivalent role. Maybe because some have a large variability, some have a small variability, so you can see or intuitively think that, okay, it does not have the same effect. But also because in the equations of the model, certain parameters have like a big deterministic sensitivity, let's say gradient, and others are completely dependent on those inputs. So sensitivity analysis really aims to clarify this and put some numbers on what are the important parameters and what not. Okay, so by the way, if you have any time questions, just raise your hand. Yeah.
Thank you. Question is, can you please share your experience how to model uncertainties in medical images, for example, which we use to forecast infarct or COVID? Or do you have experience?
No. No, honestly, no, because then in that case, the input is typically an image. So the only experience I have is when indeed the input of such a model is an image like 1,000 by 1,000 pixels. Anything that I will explain today later on with the surrogates cannot work directly with, let's say, 1 million inputs that are 1 million pixels. So that's not the same kind of application that maybe standard now deep neural network techniques can handle. So what you need in that case is some kind of compression or model reduction before you can get into it. So that's the thing we have done already, where we had models where the inputs were images. Actually, in our case, there were discretized random fields. Not medical images, but that's the same idea. It's a really unstructured, big matrix of pixels that can be combined by proper model reduction together with then the kind of techniques I will mention today. But I have not applied to what your case.
So you're from engineering school and you present how to model uncertain coefficients with PC, for example. Yeah, but do you have experience how to model data which we feed to neural network? So when we train neural networks, this data can be also uncertain.
No, because we don't do neural networks mostly. So, we have good reason not to follow the general trend that everybody does neural network and tries to do something. We have evidence that there are a number of problems, including the types of things I described today, where it's far less efficient than a good sparse PC expansion or a good Gaussian process model. We even have recent results with big benchmarks, taking machine learning benchmarks that are standard in that community, UQ benchmark, and really comparing the techniques I present today with really the standard ones from machine learning, from XGBoost to random forest to neural networks, deep neural networks. And I mean, it's clear, if you have huge amount of data, you can do a lot of fancy things with neural networks, no problem, but it's costly and takes a lot of data. And the goal of today, back to the title, is surrogate modeling. What does it mean? It comes in a few minutes. It means replacing this complex physics-based computer model by something that mimics the behavior but is very inexpensive. So that could be neural networks. The problem is that in our case, the data that we use is not collected somewhere, it's computed by the costly models. So we work in a small range of data, small number of data points, and then no way you can do something with, or something accurate with neural networks. So I will not talk about this. Okay, so back to this framework. How do you do typically these two steps here? We have at least defined how it works. Yeah.
Sorry, step C, you said that you try to establish like probability density function and so on, so characteristics of the probability distribution that you get. To what extent can you do this analytically, or I mean, you
almost no extent.
Okay.
So like a linear combination of Gaussian variables is a Gaussian variable. There are a few other like textbook exercise that tells you that if you add two, what else, I don't know, two spatial exponential distribution, you may get a gamma or something like that. But otherwise, no. Otherwise, it's numerics. Everything's numerics. So the basic brute force numerics is exactly this, one slide, very easy to understand. Monte Carlo simulation. How do you do this? To basically, as you said, find out the shape of the distribution of the output here. As you have defined, really decided what are the input distributions, you use random numbers. So you use a random number generator that produces for each input parameter numbers that are coherent with the distribution you have selected. And then you can generate a set of n different input vectors. For each input you run your model, takes the time it takes. So if you have a big cluster, maybe it's parallelized, but otherwise just taking them one by one. And then you just look at these output quantities and do whatever statistics with this. So if you have enough points, you can start with histograms and then maybe smooth the histograms and you will get the distribution. So you easily see that if you want to be accurate doing this, you will need a big number of points. And the same for computing the mean, the variance, the quantiles, the probability of exceeding certain extreme threshold. Everything is feasible. It's just a matter of this n here. If you want to be accurate, you usually need a lot of samples. But otherwise, very simple, you use a random number generator, get a long list of inputs. For each input, you run your model the way you can, and then you handle the sample of the output, okay? So it's kind of graphical representation here. Let's say it's another engineering model here with a truss structure. So for each parameters here, for the, let's say, bar parameters, loads on these things, and maybe the stiffness of the bars and so on, you just have distribution. Each time you take one value in for each distribution, you run the model and you get, for instance, the maximal displacement, vertical displacement under the loading for this structure. And if you repeat this a number of times and you have enough points here, then you can say something about the statistics. Okay, very simple in principle. If we had infinite power, computational power, maybe one day with quantum computing, who knows, I would have to change my research topic because, I mean, this is the solution if you have infinite power, or if your model is extremely inexpensive, like it takes a millionth of second to run. Okay, you can run it a million of times and that's it. So not you have, of course, to do this properly, like doing some error estimation on what you do, but I mean, it's really simple. The main problem is that if we talk about a realistic model of a realistic phenomenon, you're very happy when you already can run 20 or 50 runs. And with this, you cannot do statistics. Does it answer the question? Yeah. Okay, so Monte Carlo simulation, as I said here, it's just another summary. It's universal. Whatever complex the model is, does not play any role. It has sound statistical foundation. I have no time to explain, but again, this is very much probability 101 or statistics 101. So it's very standard things, especially convergence. If you have more points, you get closer to the true values of the outputs, whatever they are. All these runs are independent, so you can run them in parallel. And the main problem is that there is a universal convergence rate. So whatever you compute, if you want to be twice as much accurate into what you compute, you need 4 times more points, okay? And the coefficients here in front of this 1 over square root of n depends on what you compute, but can be very big. So sometimes you need really millions of such points to get something meaningful. The statistical uncertainty, that comes from the fact that if I do this here with, let's say, 1,000 points, and then tomorrow redo it with another 1,000 points, I don't get exactly the same results. They will be always different, okay? So meaning that then if I just compute, I don't know, the mean value or variance will be also not exactly the same. So that this difference is what we call the statistical uncertainty that just comes from the Monte Carlo procedure. But again, it's very, first of all, when n tends to infinity, it tends to 0. And we have all kinds of simple confidence interval modeling that allows to really be completely clear on this. So this has to be handled properly, but it's not a big issue. But the big issue is that in most problems, you cannot afford the cost it would cost to run enough times your model with different inputs such that you get accurate results. And that's where we enter into surrogates, so the keyword of this lecture today. What I call a surrogate here, I will be denoted by m tilde, is nothing but an approximation of the original model. And so what I call the model is really this map, this function from the x to the output quantities. I want to approximate it with something that will be very close in certain sense, but much faster to evaluate. Okay, so for this we will assume that this belongs to a certain class of functions with some general shapes, so certain parameterization, and then this m tilde will depend on a number of coefficients that we will have to fit to our problem. And to do this, we will base our analysis on, again, data, like in Monte Carlo simulation, so taking input vectors and the corresponding outputs. But now the difference is that here maybe we start with 10 points or 20 points. We want this done with as little data as possible, and also have methods that would work, maybe with not the extreme accuracy, but still give you something, even if you have only 10 points, okay? And that's the key word here. Those points are simulated data, so that is the costly part of the thing. In any realistic analysis, it's not anything that I will talk about today that costs time. It's really gathering, simulating the data, okay? And the last thing that we want from a surrogate is that it's fast to evaluate. That is, as you will see later, typically a function that you can run 1,000,000 times in a second with your laptop. Okay, so what kind of surrogates are popular? I will talk today about polynomial chaos expansion in all details, hopefully if I have time. So this is basically a fancy series of polynomials with certain coefficients that have to be determined. Nothing more than that. Low-rank tensor approximation is like kind of tensor product of functions, so it's a bit more general. Gaussian process also I will give, I hope, enough details today. So it's the sum of basically something that looks like this, typically a linear sum of polynomials or even linear functions, plus something that is a Gaussian process. And you see here in this column, each of these models have certain parameters. These are the parameters that you have to fit from the simulated data. So if, again, you want to talk machine learning, these are the hyperparameters of the models, and the data is what you have simulated to create information to build the surrogate. Yeah, support vector machine is already some machine learning. Of course, neural networks, this is nothing but this kind of function that you have behind it. It's not very clear or always, and it's a bit more than that in the modern architecture, but in the traditional basic multi-layer perceptrons, it's basically something like that. For at each layer, you have a linear combination of the inputs and then some activation function that can be used to be sigmoid, now it's more ReLU or stuff like that, that makes it nonlinear, and then you combine it by stacking these layers. So in the end, that's nothing more than that. And the parameters, the big difference in that case is that you can easily have millions of billions of parameters in all the layers if you have hundreds of layers. Yeah?
Do you have some experience with trigonometric or exponential functions instead of polynomials?
Instead of polynomials, we used like trigonometric functions in cases where some parameters really describe something on a circle. So you need to somehow enforce periodicity. It was the same, yeah. Yeah. That's exponential, no. That I don't know. But yeah, as soon as you have some basis spanning the proper space, in essence, should work. I mean, there's no reason not to. Okay, so the big difference again with standard data science or machine learning analysis is that we have to produce our data. So again, the constraint here in realistic cases is that you will simulate with your complex simulator inputs and outputs. So outputs given some random sampling of the inputs. But you want, with the limited information, have the maximal output knowledge. Okay, so typically here we will not use, we could use Monte Carlo simulation, the brute force one, but to design which point we choose, we try to optimize this to again get more information with limited number of points. And typically, basic thing is called Latin hypercube sampling, so it's a very simple extension of Monte Carlo sampling that can be also optimized. And there is another branch called low discrepancy sequences, which basically both try to have, with a given number of points, those points very well scattered in your input space. So if you imagine that here, in that case, that would be two parameters, x1 and x2. You have not so many points. You would like them to almost regularly fit this thing. You see that the answer is not to put a grid. Why? Because if you put a grid in 2D, it would be feasible if you have, let's say, 10 values in each dimension, that would be 100, okay? If you have 20 parameters with 10 values in each dimension, that would be 10 to the power 20 points. So forget it. It's not feasible. So that's why something based on random sampling or on these discrepancy sequences allows to fill in high-dimensional, let's say, hypercubes or stuff like that, also with very limited number of points. Okay, then once you select those points here, there is not much, but it's good to spend time to use the proper techniques again here. Then you run your model exactly as in Monte Carlo simulation before. The big difference is that before we just looked at the outputs and did some statistics after computing the outputs of a Monte Carlo simulation. What we do now is that we use the inputs and the outputs all together. That's our data set. And through proper learning algorithms that depends on which type of surrogate you want to use, then we will fit those coefficients that were listed in the table before. So for polynomials will be the coefficients. For Kriging will be parameters of the correlation function. For neural networks will be all the weights in the neural networks. Okay. What is important is that back to the philosophy, we replace whatever model M mapping the input to the outputs by a surrogate, and we want this to be very close. So we, of course, during the fitting procedure, there will be some error estimation, but this has to be in the end validated. So you have to make sure that in the end, in certain sense, this M tile is close to M. So typical standard measure is this mean square error between the prediction of the surrogates and the original model. So if you do all this properly, what you get in the end, as I said, is a function that you can run instead of running M of x, which is basically selecting x and running the complex model for hours. You can now run this and typically get 1 million runs in a second or less. Okay? If you look at the way you constructed it, it's very similar to Monte Carlo, so it's called non-intrusive. You don't have to look into the models or change equations or add something into your solvers whatsoever. You just run the model as it is. You just now select properly the inputs, but run the model really as a black box. Again, those runs can be done in parallel. And now the new challenge is that you have to be sure that this here is small enough. So what kind of measure, and if not small enough, what can you do to improve the accuracy of your surrogate before you can use it? And second thing is that to get a surrogate from very limited data, it works because behind polynomial chaos or Kriging or support vector machines and all these things, you have some kind of advanced mathematics. So then when you want to explain to people that are neither statisticians or applied mathematicians or people with some background in all these functional and statistical theories, it can be challenging because they don't believe that you can do what you claim you do. So I hope you will believe me at the end of this afternoon. Okay, so of course the goal in the end is to be much more efficient. And to conclude this part here, as you have seen, I always mention some comparison or links with machine learning because it's very similar. So in a standard, not every machine learning, but standard supervised learning, so typically you have tabular data and you want to build a model out of it. You start with a big training set here. You choose some kind of thing. So again, random forest, support vector machine, neural networks, whatever. You fit this, and then you have a validation set, and then you optimize maybe parameters so that you get the best validation error, and then you get the best model. What we have here is we start with already an existing model, not from data. Here we start from data. Here in our field, we start from a model. And we also know in which range the parameters of the model should vary, and also possibly with which kind of distributions. That's part of the procedure of the UQ analysis. So from these two ingredients, basically, we generate the data. And again, here, that's the same afterwards. But the only difference is that our point here is to say something meaningful in the end with small data instead of big data. But from here, basically, the kind of structure you could use, the way you validate, many things are very common. So that's why, yeah, it's becoming more and more close, these two research areas. Any questions at this point? General question, yeah?
Yeah, as a general question, I would like to ask if we can, in the surrogate modeling phase, can we reduce the dimension of the problem in the sense that you have an input parameters that are of dimension b, so like the compression you mentioned.
Yeah, well, in what I will tell now, no. Now, I mean, the point of this lecture is really you have m of x and you want to replace by m tilde of x with the same x's. But out of this, two outcomes. First of all, as a direct post-processing, you will easily know which of the x's could be set to a fixed value, and then this is model reduction, because instead of considering 50 varying parameters, in fact, maybe only 5 play a role, so all the others you fix to a value for future analysis, and you have actually only 5 to consider. Or, that was my first response, if you have really a high dimension, you have to do some pre-processing to compress it. Either in 2 steps. One basic thing to do this, if you have, let's say, somehow, again, images, but somehow with some structure, is typically principal component analysis. I don't know if you know that. Kernel principal component analysis if you want to do fancy, again, machine learning things. So that is more or less, you do this first, and then you do, with the reduced dimensions, you do whatever I do afterwards. Or we did this also in a more intricate way, typically use autoencoders with neural networks to decrease the dimensionality, but in a sense that not just for compression, but that you have final or intermediate latent parameters that are well correlated to the output, so that you can build a surrogate model. So that can be done, but it's beyond anything I will mention today. But this can be combined, of course. Yeah.
What's going to happen if, let's say, our physics-based model is uncertain? The physics itself is uncertain because, like, sometimes we have, like, not really a complete knowledge about, like, the physics is, let's say, this one. Maybe there is something like.
Yeah. So there is. There are many questions. Maybe we can keep this for the end discussion. But for sure, there is something that is also beyond the scope. It's kind of an extension on which we have now also many results, but it's much less mature. Is when you have in your model, it's not uncertainty in the sense you don't know. You know what's going on, but there are, let's say, hidden parameters of the model that can change from one run to the next. That we call stochastic simulator. Why? Because it means that even if you select all the x's clearly, if you rerun the model again and again, there are other internally parameters that change, and then you don't get the same output, but you get a distribution of the output. So we can do surrogates for this. This is really recent research by us and by others. I can talk about this later, but this is far less mature than what I'm presenting today. But we can do this. Yep.
Is there a thumb rule between the number of points we need to sample and the dimension of the problem we are trying to build a surrogate?
Thumb rule. Yeah, typically, I would say with those techniques, again, because if those techniques are properly applied, they are very powerful. So give good accuracy with limited data. Typically, I would say 5 to 10 times. So again, you have 10 parameters. You can usually start with 50 points, 100 points. And then, as you will see later, you get measures of how accurate your surrogate model is. So maybe in certain cases, 50 points already, you get 10 to the minus 6, so you're happy. Maybe it's a bit more tricky, and then you would need 300, 400s. But you have error measures that tells you how much you should add and until when to go so that you can validate your surrogate. So that comes also as part of the game. Okay, so the rest of this lecture, and probably we'll stop for a break before the end of this remaining 70 slides, of 60-something slides, is about polynomial chaos expansion. So I will introduce the general idea, how to basically compute those coefficients that you have seen already. Then address what we call the curse of dimensionality, so how to use this when you have not just 2 or 3 parameters, but again maybe 50 input parameters, and then I show some examples. So at least in the beginning here in the first slide, we will assume that we have d input parameters, each of them with a given distribution that has been solved beforehand. And we assume they are independent for now. Of course, we can handle statistical dependence and correlation, but let's say it's independent for now. Basically, the theory, and we have a very good expert in the room here, is that basically we expand the output random variable, or each scalar component of this output, as a polynomial series of the input. And these polynomials here, I will explain in details, there are multivariate polynomials of the input variables with certain orthonormality properties. And you see here there is an equal. So at this stage, this representation under very mild assumptions, basically that you have a finite variance here, it's exact. But this series is an infinite series. So of course, in practice, we handle only a finite number of terms and coefficients, and that's where the approximation comes from this truncated series, and then from the way you compute the coefficients. Before getting into the math, I'd like to also intuitively show you why, if it works, will be much more efficient than Monte Carlo. So I have taken a very simple model that will come back also in the end here. It comes from a very simple geotechnical problem. You have some soil with here very, again, simple soil with 2 properties that define basically its resistance, the cohesion and the friction angle. You want to put a building, so you put a foundation, and you want to know the maximum bearing capacity of this foundation, design how big should be the foundation to have a tower of 20 stories, for instance. Okay, so very simple model will give you this bearing capacity, this maximal pressure before the soil collapses, as a function of these 2 parameters. And in the simplest case, it's an analytical function that you will see later on. Okay, and it looks like this. C is in this axis, so you see a bit flat, not so dependent. And here a big increase as a function of this second parameter phi. If you wanted to explore what's going on now when C and phi are uncertain and have certain distribution, well, basically according to these distributions, you would sample points and then evaluate this model and get the corresponding bearing capacity. But in practice, what you get is really this. You don't know that there was a surface in general, because you have more than 2 parameters, you cannot plot it. So the only thing you know is, okay, I can generate easily this cloud of points. It's quite easy to understand that if you really want to find out that it looks like this blue surface, you need really many, many points, especially if you want to know what's going on in the extremes here, and those extremes are very unlikely, so you need many points to have also a few points in the extreme corners, okay? So that's Monte Carlo. What is PC expansion? Basically, it says, okay, there is an underlying surface, in this case, function of 2 parameters. I will expand this surface as a sum of coefficients times basic surfaces. And you see in that problem here, it looks nonlinear in the 2 dimensions, but I mean, it's not crazy oscillating and nonlinear. So basically, and it's also generally the case. So just with a few such superposition of basic functions, which are nothing but the graphic representation of these polynomials I mentioned, multiplied by a few coefficients, maybe here 10 or less, you can get almost exactly the surface. And if basically representing the surface now, instead of boiling down to millions of points, boils down to 10 coefficients, you can imagine that you need little information to compute these 10 coefficients. Okay, so that's the whole principle of PC expansion. Yeah.
Can you please come back to Monte Carlo?
Yeah.
Yes, this one.
Yeah.
Yes, exactly. Assume that I would like to forecast some rare event, so some certain small part of this
Yeah.
manifold.
Yeah.
So with Monte Carlo, I need certain certainty to fit this. But do I understand correct this that if I take let's say tensor mesh, I can use polynomial Gauss expansion very efficiently because I can take very fine mesh and with very certain hit.
You don't need to take a mesh. You can, as I said, the data we use for the polynomial chaos expansions are exactly those points, but far less, but exactly, could be exactly the same points, except that from those points here, you try to guess where is the surface in Monte Carlo, whereas with polynomial chaos or other surrogates, from those points, you build an analytical function and the points serve to fit the coefficients. And so that's, you come back to a continuous representation instead of a point by point.
I'm sorry, I formulated it wrong. Does surrogate model offer certain advantages by forecasting rare events or not?
Yes, we will see this with the next presentation because if you want to capture what's going on in the corner here, you want to be your surrogate to be accurate in the corner here. Not necessarily everywhere, okay everywhere, but very accurate in that corner. And so this brings to the topic of what we call active learning, where we will start with a few points, far less than those, but then instead of adding points everywhere, like extending Latin hypercube, we have techniques to add new points in the region of interest of the rare event. And that is called active learning, very general also in machine learning. So I will show this in the second presentation. Okay, so let's try to now summarize. So we want to have this kind of representation here. By the way, if you consider that your output is a random variable as an abstract object, whatever it is, I'm not a mathematician, but okay, I see whatever it should be, or I have an intuition of this. What we do here is represent this in a given space. In fact, it's very well posed. It's a Hilbert space of, let's say, square integrable functions somehow. So you can imagine this here as something that you would represent on a basis, exactly as in our 3D world, we represent the position of any points with 3 coordinates. Here is just an infinite dimensional space that is suitable, so there is an infinite number of coordinates, but with a finite number of them, because there are some additional things, so just with a limited finite number of them, you get a very good representation. So you can really think about this. The psi alpha will be somehow a basis to represent our fancy output random variables, and the y alpha are really coordinates, because again, there is a keyword somewhere, we have an orthonormal basis. So it's really like Euclidean space. Okay, so the steps to get there is, first of all, how to construct this basis, then how to compute the coefficients. As I said, there is some kind of approximation, so how to check how accurate it is. And even if we do all of this, the questions, let's say engineering question or practical questions, is not to get this fancy thing, is to get information on the statistics of this. So even if I do this, how do I then get the moments, the mean, the standard deviation, quantize the PDF, the maybe sensitivity indices out of this? So that will be the final, let's say, post-processing of this. Starting with the basis, so there is a bit of functional analysis here, but you can also skip it. You don't really need to know all the details to use it in practice. So if our input vector is based on different independent input parameters, so the joint distribution is basically the product of the distribution of each parameter. So for each input separately, we will define this functional product here, which allows us to define what means orthogonality of functions. So basically, for any two functions, if this integral here, the integral of the product multiplied by this weight, which is the PDF of the input, if this is 0, we say that they are orthogonal. And there is a very classical theory to start from polynomials, so like 1x, x squared, and so on, and make them orthogonal with respect to whatever weighting measure here. So, I mean, it's known since the 19th century. There are books with thousands of pages with all the fancy and incredible properties of orthogonal polynomials. So this is really completely well known way before people did uncertainty quantification. Okay, so with this, basically, with some numerics, we can build this so-called orthogonal polynomial in one variable. Actually, as I said, it's so well known that for a number of very standard input distributions, like small here, but you can read maybe uniform, Gaussian, gamma, beta distributions, for all of them, those polynomials are known analytically. You can really generate them analytically, and they even have names according to the guy who worked on, the mathematician who worked on those polynomials first. So you see all their picture. It was not so funny when you look at them, but and when you read the books, you understand it. But I mean, it's okay. It's very classical. I think any master in applied mathematics basically knows all the details of this. So it's really, really well established. You have some details in the appendix if you are curious about this, but we don't need more than that. Yeah, yeah.
Did you observe some cases when, let's say, Laguerre is working fine, but Hermite not, and Jacobi again fine?
Again, the optimal thing is to choose the polynomials that are orthogonal to the input distribution. As the input distribution is given by your problem, well, then it's set up. Then, of course, you could say, well, there is at least one case where you have to do this. If your input is a so-called log normal distribution, there is a fancy mathematical complexity there, so you cannot find orthogonal polynomials. So then you have to say, okay, the log normal is the exponential of a Gaussian distribution, and so you introduce a change of distribution in the game. So which is for log normal is kind of mandatory. So you could do this in general for other things, and usually it's suboptimal. What is optimal is the orthogonal with the real thing, which means also, it's probably written somewhere later, if you have now a lot of input data and no classical distribution fits well your data, maybe it's bimodal or fancy, but you have enough points to really see what is the distribution, we can also do this with non-parametric distributions. So we compute orthogonal polynomials orthogonal to non-parametric distributions if we assume that this represents properly the input, and this works. So, yeah.
So it means that taking one or another family of polynomials, I may have less or more coefficients.
Yeah. Okay, when we have this, so for each type of inputs, so let's say all our input parameters, we decided they vary in a range and we assign them a uniform distribution, so we will work with a single family, which is called the gendre. Now, how do we get the basis? This is basically multivariate polynomials, and this is just this simple equation. So it now depends on all the inputs parameters, and it's just the product of the univariate polynomials that we have defined before. So and those depend on the type of the input distribution. So if all input parameters are uniform, let's say, then all these polynomials with different degrees, they will be all from the same Legendre family. If now I have two different inputs, one Gaussian, one uniform, then we have to choose different. So I will show an example in a minute. And here you see that then this multivariate polynomial, they are defined as product of univariates. So what matters is which are the degree of each of the univariates. So we map one-to-one those polynomials with basically a multi-index. This length here, these are all integers, and the length is the number of input parameters. That should be D here. Sometimes it's D, sometimes it's M. It's not always completely coherent, I'm sorry. But anyway, these are integers that corresponds to the degree, the partial degree of the polynomials obtained this way in each of the input parameters. And the point is that when you use this kind of basis, mathematicians proved that you really have a basis of the space of random variables you want to represent. So if you have the infinite set of terms, you really have an equality. So this looks like this here, typically a 2D polynomial with two inputs, x1 and x2. You obtain the surfaces I've shown before by just the product of, let's say, this one would be linear in x1 and linear in x2. This one would be constant in x2 and quadratic in x1, and so on and so forth. This one is third degree in the 2 dimension, and so on. And you can go as high as you want. Typically, all those polynomials, when you increase the degree, they will oscillate more, and that's the way you would capture details in the underlying function you try to represent as a superposition of those functions times coefficients, as I showed in the beginning. What time is it? Some details. These are really details. I will go quickly, but as I said, if you have variables that are not from the standard families, you can use what is called an isoprobabilistic transform. So, for instance, here, if you have, let's say, a variable with a given distribution that is complex, you can transform that input distribution given by this, or defined by this CDF f here, into a Gaussian variable by simply mapping back and forth the CDF and inverse CDF. And then this means that basically you just introduce auxiliary parameters in your problem. So instead of working directly with polynomials of x1, x2, you work with polynomials of auxiliary variables, but they are one-to-one mapped to the physical ones. As I said, you can also do numerically polynomials orthogonal to anything that can be computed numerically, especially to also non-parametric distributions. And that's also the way we handle the dependence that I mentioned, and then I said, let's forget it for now. So if you have dependence, it means that there is some joint correlation between the parameters. So all the input parameters all together, the input random vector, is defined by a distribution that is not just the product of the marginal distribution, but something that couples this. And you can represent this with the so-called copula theory, which then brings you to something where, well, all the components are correlated. So if you are in this case, you cannot directly apply this construction I mentioned just before. Again, you have to introduce auxiliary variables that are independent, and there are ways to map this joint distribution into independent variable so that you can come back to the independent case and then apply this technique of orthogonal and multivariate that I've shown before. Okay, then you have another question that I will come back again and again, which is you have to truncate the series. You cannot handle the infinite exact series, you have to truncate. So the first and basic idea as we work with polynomials is to take the total degree of the polynomial. So that would be, you remember, it's a product of univariate polynomial. So I will call total degree the sum of these partial degrees in each input. And so one idea to truncate is to select all the possible polynomials such that the total degree is less than 3, 4, 5, whatever. Okay? So this way, you basically use the polynomial degree as a kind of indicator of how complex or how big you want to have your truncated series. We will come back to this later on. Doing this basically very soon, that is for low degrees and quite low number of inputs. M is again a number of inputs. When it's not D, it's M. You basically have this big number of terms in the expansion, and that explodes very quickly. I will give some number later on. But if we have, let's say, few variables and polynomials up to degree 3, why not? We could do this. This I represent, that's also a view that is useful. It's now here the degrees of the polynomial. So in 2D, there would be 2 variables, and we'd have polynomials of degree alpha 1 in the first variable and alpha 2. So each polynomial in this basis is basically corresponding to 1 point on this grid, which is the 2 degrees. Okay? So what happens is when you increase the total degrees, basically you move from all polynomials up to degree 3, 4, 5, and 6, and so on. You see that you expand it. And you can imagine that now if this grid is not just in 2D but in 20D, this explodes in the way it expands. Yeah?
Is there, let's say, smarter way of using this
yes.
truncation?
Yes, come soon. Be patient. Okay, so here I just want to point out that there will be some curse of dimensionality, so explosion to handle, and we will handle this very soon. I show you an example, so a problem again with whatever model, but there are only two inputs to just write you all the details. So let's say that we have two inputs. The first one is Gaussian because I have data that shows, okay, it's Gaussian, it's some kind of uncertainty is Gaussian. Second one I don't really know, but I know bounds, so I put uniform. How do I do all this? So first thing is to transform the Gaussian in the uniform into standardized variables because those Legendre or Hermite polynomials, there are the analytical things you find in a textbook, they are related to the standardized variables. So here it's very simple, it's just a linear, stretching and translation to represent x as a function of a standard normal or x2 as a function of a standard uniform. Then you choose the right family, as I said already, and then you get the bivariate polynomials as product of the two. So if I want to take now all those polynomials in two variables up to degree 3, back here that would be exactly those 10 points here in this representation. This leads to 10 polynomials, and you see here this is explicitly the equation of those polynomials in x1 and x2 with increasing degree. With one color corresponds to x1, to the Hermite, and the green color corresponds to the Hermite. And so at this stage, whatever the physics, the complexity of the problem, just because it has two inputs and I have said what are these inputs, my representation will always be, if I choose degree 3, a polynomial series with those 10 terms. And the difference now, if I do geophysics or mechanics or chemistry with two parameters, is just that, of course, the coefficients will be different because it depends on the problem and the data. But the basis is the same. You had a question? No, sorry. Okay, is it clear how we build up the different things? Yeah, so just conclusions, who cares? That's just summarizing what I just said. At this stage, now we have a basis. Now, next stage is to compute the coefficients, and now this is problem specific, okay? We will, for a given problem, run our simulator, get some data, and we want to fit the coefficients of those polynomials so that we get a surrogate. So, historically, people use these techniques of polynomials all together with the equations. This is called like Galerkin stochastic methods or intrusive methods. That was basically very active 25 years ago, up to maybe 15 years ago. The problem is that it's very powerful. It's somehow equivalent. The problem is that, as the name says, it's intrusive. So you have to get into your solver, into your equations, introduce the stochasticity there, and resolve the thing. And yeah, for any new problem, basically, you have, or any new governing equations, you have to redo this. So it's less and less popular, especially because now what we call non-intrusive approaches that exist also for 20 years, they are based on data, and now they are basically exactly the same paradigm as machine learning. So basically everybody wants to do this. So in this non-intrusive approach, that's exactly what I have presented in the general, let's say, frame for surrogate modeling. We will just generate data, take some x's, well chosen, compute the output, m of xi's here, and then from this, then basically find methods that computes the coefficients. So again, there is a long list of methods here. I will just, because of sake of time, talk about, first of all, something called basic least square, and then extend to so-called compressive sensing. So in the basic, in this basic approach here, which you will see in a minute, is nothing but least square minimization. It's quite simple, also intuitive to understand. We have an infinite series that will give us the exact surrogate, okay? If we truncate it because we need to, then we will left apart a big number of terms, so there will be a residual. So we will consider this exact thing as my truncated series plus a residual. The series of interest has, let's say, p coefficients that are my p unknowns. And the idea is basically to find those p coefficients such that the residual, so what I left out, is the smallest possible. Very simple. Okay, so I want to minimize the residual between the true model prediction and a truncated series for which now I know all these terms here. These are the polynomials. Now they are not called psi alphas just because I numbered them from 0 to p, but that's the same psi alpha as before. Okay. Now the question is how to compute those coefficients. Okay, so well, simple measure. Let's try to minimize the mean square error of this residual. And this is basically minimizing this mean square term here. If we solve this, so this is nothing but a quadratic function of this unknown y coefficient that are gathered in this vector. So this is a quadratic expression. You differentiate it and set it to 0, and you basically get the solution. And the solution is, it's basically, each coefficient is the expectation of the product of m times the psi alpha. So I don't know if there is, yeah, I don't want to go back 15 slides before, but if you remember my representation that basically somewhere here I have y and this will be psi 1, this axis will be psi 2 and psi 3. What this equation says is that the coordinate, let's say a3 here, because of the orthogonal basis, is nothing but, well, the projection of this onto this axis. So that coefficient here is basically y multiplied by this basis function. Okay, so that's nice, but it's not so easy to compute. So how to compute this expectation? There are full literature on this, where basically if you write what it means here, it's just a multivariate integral. So there are ways to compute very efficiently multivariate, include the high-dimensional multivariate integral with sparse grids and stuff like that. So that's one way to do. The other way is to come back to more machine learning view and say, well, I have generated data, or I can generate data. How could I use it? Well, you basically replace this mean square error, which is really the average error, by just the empirical average error on the data at hand, the data that you simulated. Okay, so basically replace this. And again, here, now in this expression, the only unknowns are all the coefficients, and it's a quadratic functions of those coefficients that you see here if I expand everything. So minimizing this is exactly, in fact, a least square, ordinary least square problem. So if you have used it already, you probably know the answer of this. If you want to minimize the difference between certain points and a function or sum of function parameterized by coefficients, you basically need these terms here, which is the experimental matrix. You need these here. These are the evaluation of the true complex model on each of the xi's. And the solution of this is basically, and I will not do the math, you can do it in details by yourself, will be basically a linear system where you have this matrix A. So by the way, A here means for the truncated series I have selected, the values of all the selected polynomials for all the points in my input experimental design. Okay, that's A. And the solution for the y coefficients is basically solving this linear system. Yep.
So can you please come back to the previous slide? Yeah. Or the previous one. Yeah. So one of our issues at the beginning is that maybe the cost of the model, the computational model, is
big.
Is too big, right? And we try to introduce the surrogate model.
Yeah.
But then coming back to this, to solve this, we need actually to calculate the output of the computational model.
Yeah, there's no way. I mean, you need some data to train whatever model. So the big difference, again, is that if you can afford only 10 such runs, so that would be this 10 m of xi, you can already do something. Not necessarily just the least square, much more advanced stuff that come later. But with 10 points, you can already do something. Okay. But if you have 1 point because it takes a month for 1 point, well, come back in 5 years when computers are bigger to do UQ for that problem. I mean, of course, you need to generate data. But not millions of such runs, but maybe 10 or 50 works.
And also, can we evaluate how this minimum
minimum number of points or what? Minimum?
No, the minimum of this, the argument, the
Yeah.
solution of this problem, which is the y hat, how does it vary from the input xi's that you are choosing? Because you're sampling, right? It's
Yeah.
sample xi's.
Well, that belongs to the error estimation that also comes to in a minute. Okay. It's really, yeah, how basically changing the x size would change the results, basically. Yeah. So that comes with the error estimation in a minute. Okay, so now summarizing this really in just one slide, we selected like polynomial representation. We saw how to build the fancy basis. Now to compute the coefficient, we start by sampling points, let's say smartly, so that it's really covering well the space where you want to do the surrogate, so the input space here. We run the thing, so again, the only point here is that you don't need thousands or millions to start with. You can start with very limited, but still you need more than one. And then you solve this problem and you get the coefficients. I will not get into much details, but I mentioned already that the typical designs we could use that also, let's say, scale with the dimension, not just for 2D, but for 50, 100 parameters, which would be like an hypercube of dimension 100 in that case. We can start with Monte Carlo. Why not? For high dimension, this is somehow the method that has no drawbacks. It has the same properties in 2 or 100 dimensions, more or less. So for high dimensions, very often we would use Monte Carlo. But otherwise, we try to optimize the coverage of the space with limited number of points with Latin hypercube sampling or such patterns here, like low discrepancy sequences. Yeah?
So if you, let's say, if you have like an extreme distributions like the GEV, the generalized extreme value,
yeah.
is it enough to just sample it with Latin hypercube?
I mean, it's independent. Latin hypercube is a technique that allows to sample in an hypercube, as the name says. So if you have any kinds of distribution, you have any way to transform points generated over 0, 1 into the distribution with this inverse CDF transform. And this is universal, works for any types of distribution, even fancy ones with extremes or fancy family. Because those points on 0, 1, 0, 1, they will be mapped to the extreme because of this inverse CDF. Okay? Yeah?
But you need to sample these sequences from the distribution of the input, or do you always sample uniformly?
No. You need, right, it was a bit quick. You need to sample with the input distribution to generate points that are relevant with the input distribution. But most of the techniques, they will first sample uniforms and transform them. So Monte Carlo, even basic Monte Carlo, if you want to sample a Gumbel distribution or a GEV, general extreme value, you have the CDF expression. So the standard techniques, you sample a number between 0 and 1, which is uniform, and you use the inverse CDF, and like two-line proof shows you that it follows the right distribution. So that's always the way, in most cases, the way it's done. You sample uniforms, and then you back transform them into whatever distribution you need. And now the way to sample uniform, you can really do Monte Carlo uniform or a bit optimized uniform. But in any case, you indeed resample them to the right distribution.
I'm sorry, stupid question. Till now we decompose or represented random variable in certain bases, yes? Random variable C in Hermite basis, let's say, yes? So question is it some advantage to represent density or distribution function?
Instead of the, well, that's what people did in the 70s. There are all kinds of series expansion, Edworth, and things like that. The problem is that a PDF must be positive and integrates to 1. So expanding this kind of function, even with constraints, you always get bad behavior. And so that was used in different fields, and I think it's abandoned because that works much better. You expand you expand the variable, not the PDF of the variable. So as far as I know, yeah, no, it's not really useful anymore. Okay, let's go forward. So we have this fancy representation. Practically, we have just a truncated series. So this just means that we have a finite set of terms. And as I said, now we have at least a basic way of do all the steps up to get there, get the basis and get the coefficients. So how now do we come back to the uncertainty questions? That is, as I said, how to compute the mean, variance, quantize, PDF of this output and whatever. One thing that is very nice with the effort we paid to construct this orthogonal basis, which is a bit fancy, I agree, is that now the coefficients, also what I display here, they have a meaning. And for instance, the mean value of the output random variable y is exactly the zero coefficients of the expansion. So there's nothing to compute or to post-process. That coefficient is the mean value of your surrogate. And the variance is the sum of the square of the other coefficients that you have computed. And if you go to higher statistical moments, again, you have combinations of powers of the coefficients. So in other words, you really have this complex thing that is a distribution is completely represented by the coefficients if you add the infinite series, or more or less accurately represented if you just have a finite series of coefficients. And all the information is captured there. So then just by post-processing those coefficients, you get all the statistical information on your output. Okay, so these are higher order statistics, not so interesting. Now, if I want really to plot the output distribution, how do I do this? Remember at the beginning, this fancy animation with the small truss structure, I told you, look, this is the principle of Monte Carlo. If I use really many, many points, then I have a big output sample, and then I could plot an histogram. I could do something more, which is basically a smooth version of histogram that is called kernel density smoothing here. But with many, many points, I can really get the distribution very accurately. Why don't I do this in practice with my model? It's just because if I have a big model, I cannot do a million Monte Carlo. Okay, I cannot do this. But now with the surrogate, well, the point of the surrogate is that I can do a million simulation, Monte Carlo simulation of my surrogate, of my polynomial in a second or less. So why not do it? Again, if we have no issue with computational cost, forget everything I say, just do Monte Carlo. That works. It's just about computational cost here. So to get now the PDF of the output, what we will get is actually the PDF of not y exactly, but the PDF of that guy here. But that we can get almost exactly at no cost, because we can run this million times and plot the histograms or distribution. So that's what is written here. You just take a big number here of samples, and you use your polynomial with those samples, and then you represent an histogram or this fancy thing here, which is nothing but a smoothed version of the histogram. So this allows to get a very smooth function that really looks like a distribution. Okay? So that's how to get distribution. Yeah?
Yes. Am I right that every next term is computed less and less accurate because corresponding polynomial degree is higher and higher?
This may be the case with, again, integration techniques, but not here. Here there is no... yeah, okay, if you get into the error estimate or the variance of the coefficients, it may be less accurate, but what counts is not the accuracy. What counts is the magnitude of the coefficients, as you can see from this equation here, and that is also what leads us to sparse expansion later on. For the variance, so the variability of the output, it's the sum of the square of the coefficients. So if you have the very small coefficients that are not so accurate, for the quantities of interest, they play no role, in fact. And that's the same for the sampling. So even if it's probably true that you have less accuracy when you use a limited experimental design to compute very small coefficients, because they are small, it's not a big issue for the quantities of statistical quantities of interest. Yeah? Oh, sorry.
So, sorry. Would you mean that the higher order coefficients contribute less to the global.
You will see this also in a minute. Yeah.
I'm sorry.
Yeah.
Second half of question. So
We are probably here until 7 p.m. Be ready. So.
two possible errors. When I truncate too early this series, so some important
Yeah.
coefficients are cancelled. And every single coefficient is computed not accurately enough.
Yeah.
What is more dangerous?
I don't care, because what I will get also very soon in the slides is the global error. And I don't care in practice if the error comes from one of the two sources. You're right, there are the two sources. But the error estimation I will get for these kind of things is a global mean square error. And that I can monitor, I can squeeze down to whatever threshold I need by putting more points or by being more increasing the degree. And this is what I can monitor. And so the fact that what contributes to this error is because I don't have enough terms or each term is not accurate is automatically embedded in the way I compute the term and the errors. So I don't need to justify where it is. Also now another application, I mentioned at the beginning that as soon as you have complex models and you start varying parameters, so this is very completely general purpose question. Complex model, let's say 20 parameters, more or less you have a range for each of them. You are usually interested to know which parameters really influence the results, okay? And empirical answer to this question is, in almost all cases, it's just a few of them. Not the 20 or the 50, but maybe just 5. I have examples also in a minute, or in the end. And so it's important, or it's very informative to find out which ones are those parameters that really influence what you compute and the output, because the other ones that may be not well known and uncertain but have absolutely no impact on the output, you don't care. You take a value, reasonable one, and anyway you could change this value that does not affect at all the predictions. Okay? So the tool to handle this, that is what are important parameters, is so-called global sensitivity analysis, and the standard, there are many techniques, but the standard ones that is the most used in, let's say again, standard problems, does not solve everything, but solve probably 90% of the problems, is the so-called variance decomposition. So the idea is that you have this output distribution, now we know more or less how to predict it. It has a certain variability. The variance decomposition techniques, it's also what is called ANOVA in statistics, it's exactly the same, is to try to find out which parameter, what is the contribution to this output variance of each of the input parameters through the model. And more than that, also if there are like kind of joint contribution, joint effects, maybe third order effects and so on. And the tool for this, or the powerful mathematical result, is the following. Again, any model, let's say defined with uniform inputs, but that generalize to any kind of distribution provided we have independent inputs, that is the important thing, but with any distribution. This can be expanded as a constant plus sum of univariate functions that depends on each inputs, then bivariate functions, and then higher order terms. This decomposition is quite magic, it's unique. All the terms here are orthogonal in the same sense I defined orthogonality before. And then somehow they contain more and more detailed information of the output. So as basically this exists, it would be complex to compute, but in practice we don't compute it. We know we can prove it exists. Now if I compute the variance of this, so X is now, let's say, set of independent inputs. If I compute the variance of this with this big series, what I get is the following. It's the variance of the sum of all those terms, and because of orthogonality that can be shown, it's just the sum of the variance of the term. There is no cross covariance, okay? And so if I normalize each of these terms, that is the variance of each of these terms of this long series, which in practice would have 2 to the power n terms, but we of course don't compute all of them. If I normalize them, then that is exactly what is defined as Sobol index. This is the percentage of the output variance that I can attribute to each single input. And this being said, what remains for each interaction pair by pair and then triplets interaction, and so on. Okay? So first order indices is really the direct effect of each of the inputs, so that will be basically related just to those terms here. By the way, if the model would be a linear combination, then the decomposition would be exactly this, and this variance decomposition would be basically, well, taking here the variance of each term, which is, again, very, very standard measure of sensitivity for, let's say, linear systems, but linear models, but here it's general purpose. And then we also define what is called the total influence of each parameter, which will basically, in this expansion here, if I take x1, we'll take the term number 1 here, then we'll take all the terms x1, x whatever here, and here we'll take x1 and 2 other interactions, all of them. So again, in practice, in most problems, not all, but 90-something%, most of the variance or most of the important terms are basically in those terms, maybe sometimes with the second order interaction, but anything here which there is a long series is almost 0. So it's not that I would like them to be 0. They are 0 in practice. Okay, so but anyway, we can compute just the first order impact or effect, and then there is a way to directly compute the total order. So basically, if those two are very close, it means that, it means that most of the interesting stuff is there and anything there is negligible. Now back to PC expansion, because sensitivity is also, was or is still a very dynamic research field, but all this idea of variance decomposition, they are more than 30 years old now. And for at least 1 decade or more, people would try to compute now practically these indices that contain really interesting information, again, just by Monte Carlo. And as in any other application, Monte Carlo is very inefficient, and people try to make it a bit more efficient. Up to a point where we managed to see similarities between all this theory of variance decomposition and all these orthogonal PC expansions. And in fact, the common term is orthogonality. And basically, if you consider now that your model is a polynomial chaos expansion, so this sum of terms, this fancy decomposition for the sensitivity is fully analytical. And the variance of the terms that leads to these sensitivity indices boils down to computing variance of, let's say, sub-series of the series expansion, such that it's also fully analytical. It's again boils down to sum of squares of the computed coefficients. So in other words, once you do PCE, you have the full sensitivity analysis at any order for free. It's just computing sum of squares of coefficients. So this is one of my favorite paper, and it's by far my most cited paper because, well, when people realize this, then they use it. It's very simple. And how do you, well, what are the coefficients that are behind this fancy mathematics here? It's very simple to understand. If I want the effect of variable x1 in all this expansion, I will just take all the terms where there is an x1 variable in the polynomial, and then if the polynomial depends only on x1, like something x1, something x1 square, x1 third, whatever, but just on x1 and no other variable, just taking those terms and the corresponding coefficients, that leads me to the effect of x1, nothing more than that. If I want the total effect of x1, I will take all the polynomials that have at least x1 to a certain power, so there are many more, but still, yeah, finite number, so it's still a truncated, it's a sub-series of the truncated series, and then I just sum them, and that's it. Okay, there will be an example again about this in the end. Any question at this stage? Or do you want to make a break, maybe? I don't know. Yeah, question?
Can you comment on the dimensions? Like, can you have a d-dimensional parameter for a model which is giving us some other k-dimensional output?
Say it again. So what?
Does the dimensions of the input and output need to be same, or could we have different dimensions?
No. Everything that I present now here is whatever dimensionality of the inputs, again, reasonable. Let's say from 1 to 100, let's say. And the output for so far is just 1. But the thing is, what you do for one dimension, you do the same for any output dimension. So if you have 100 outputs, you just do this 100 times. It's so quick and efficient that you just do it for each dimension separately. Okay, if you have, let's say, 5 outputs that are really 5 different physical quantities, you do this 5 times, full stop. If your output is like a field and you have, in fact, 1,000 quantities because it's the nodal values computed on a mesh, you could do this 1,000 times, but okay, now it becomes a bit more expensive to fit 1,000 polynomials. And that's where, again, you do some kind of compression, this principal component analysis, which will reduce these 1,000 physical output quantities to maybe 10 abstract variables multiplied by 10 modes or shapes, and you basically, or 5, and then you just have 5 PC expansions to do. So if you have a large output dimensionality, usually there is a structure, and again, this compression works before you do this. And this combines very, smoothly. And this is what people in other communities call reduced order models, proper orthogonal decomposition. That's exactly the same. That was developed in different communities in parallel with different wording. In the end, that's exactly the same. Okay, so we have really all the ingredients to start with a problem and get some kind of solution to get this polynomial chaos expansion and this surrogate. But if you want to do this in practice just with the tools I've mentioned so far, at a reasonable cost, again, it will be limited to very few parameters and not to nonlinear problems. So the second part of the lecture is now to make it much more general with this new keyword, which we call sparse expansion. Okay, so one question also that was not addressed is how to validate. So I replaced the true model by a surrogate. How can I make sure that it's accurate enough? Okay, and again, for a long time, people would just take all the polynomials up to a certain degree because it's a natural way to truncate, and then change the degree. So if you have a higher degree, you have more terms, more efforts, or you need more data to compute those terms, and then somehow check the convergence, okay, and stop somewhere. So what has been done in the last decade or so is really go for real error estimation in an efficient way. And here I need to define a few terms, starting with what people in machine learning would call generalization error, which basically is what we should estimate. So it's really taking all possible input vectors, the mean square discrepancy between the true output and what is predicted by the surrogate, average over all possible inputs. That's the so-called generalization error. Or validation error, if you want. One way to compute this, well, also very easy, you take 1,000,000 Monte Carlo points and you compute the two terms, the mean square error, and then you get it. Okay, but to do this, you need 1,000,000 evaluations of the complex models. So if you came to the idea of a surrogate because you can't evaluate more than 50 models, you will never use here a real big validation set, okay? But in principle, that's what we would like to estimate, because that is the error of the surrogate. Something that people did also at the beginning, which is completely wrong to do, is to say, okay, but I have data. I have the data that helped me to fit the coefficients of the polynomial. So once I have the polynomial coefficients, just put again the data in this here and compute this mean square error on the training data. This is called the empirical error. This is what you would do when you really do statistics with noisy data in regression. But that does not work for our surrogate modeling thing, because it's severely underestimating this thing here. And this phenomenon is called overfitting. What does it mean? It means that you could easily achieve, for the points of the training set, a very small error between the true value and the surrogate. You could even get 0 if you use certain techniques that would interpolate your data point. That would be exactly 0, because at all the points you use, you interpolate, so the two are equal. But this does not mean if you interpolate, that in between or for other points, the error is 0. It's actually not. So this is what we call overfitting. Okay, so you can see this here in a very well-known and simple example. It's a 1D function, which we try to interpolate with polynomials. And you put more and more points. So you start with 3 points here, and this is the blue curve. So with 3 points, you basically fit a parabola. It's not very good. Okay. If you put 5 points, you could get a polynomial's maximum degree 5.4. That interpolates the data. And if you put more points, again, at each step, you can find an interpolating polynomial. I mean, that's standard interpolation. So on those problems here, where you have a single x dimension, in each possible curve I have shown, that is exactly 0. This empirical error is exactly 0. Now, the true mean square error is basically, well, the area between the original blue curve and any of the other curve. And you see that because of the higher degree polynomial and oscillations, it gets worse and worse. Okay? So and this is exactly overfitting. We exactly fit the data points, but if we take any other points that is not one of the blue points, the error between the true function and the surrogate can be completely huge. Okay? So we want to avoid this. And certainly it's not by making this quantity small that we manage to get this okay. So that's where, again, we learn from statistical learning or machine learning community, where people don't have all these fancy polynomials, but still they have data and they want to fit a model and they want to validate. So what they do, and this is basically, again, kind of the very first rule to have in mind, you always split your data into a training set where you fit whatever you want, and then you validate on completely independent data. Because if you use the same data to see how accurate your model is, it can be very accurate on the data used to learn the model. And this is exactly overfitting. It's very good for the data you use to fit, but if you take any other data that is supposed to be similar, the predictions are very bad. So to avoid this, basically, you split into 2. And, but then it's, of course, feasible, and maybe you know that people typically use 80% for training, 20% for validation. Again, I don't know why, but that's standard rule. But doing this, it's okay if you have a large number of points. So somehow you can waste 20% for validation. In our context, we want to start maybe with 10 points. So if you, or 20 points, if you want to fit a surrogate with 20 points compared to just 12 or 15, it's a big difference in terms of information. So we would like not to kind of waste information for validation, but still we want to do validation. And the trick here, what we use is so-called leave one out cross-validation, or generally k-fold validation, but in our case, leave one out is what works well. We will try with a limited set of data to mimic an external validation set. And this is how it works. So we have this experimental data set, okay, with n not big. So if I don't want to remove 20% of those points to compute my error, so what I do is the following. I remove 1 point. So this backslash means all points but 1 point. And with the n-1 blue points, I fit the best possible polynomial chaos expansion, either with the techniques we have seen so far or the techniques we'll see later. And then for that just single red point, I compute, basically I have here n-1 training points, 1 validation point. And I can, it's independent, so I can compute just one single error between the true value at that red point and what would be predicted from a polynomial chaos built on the blue points around. And then I can just, of course, change the point, do this n different times, and sum up those mean square errors computed this way. Okay, that in statistics, also known from the 70s, is called predicted residual sum of square, and in modern terms, that's the leave one out error, because basically we always leave 1 point out, and then we do a model that does not take this point and compute the error just on this point. Okay. Okay, so that leave one out is defined here. It is the mean square error on all points between the true value and the value predicted at that point with a PC expansion that would not take this point in its learning set. Okay? And we always also like to talk in terms of relative error, so usually we normalize this by the variance, so we get here like percentage or something. So if you followed me up to now, you said, okay, maybe, and I tell you, this is now a good approximation of the real validation error, at least much better. But if you followed me, you said, okay, but now instead of computing one PC expansion, we need n different fittings, which, okay, gives some nice error estimate, but comes at the cost of being n times more costly. And that's where, because of the structure of the problem and nice algebraic properties, in fact, we don't need to do this. To compute this error, so really I don't change the definition, what we do in practice is we do a single PC expansion with all points, and the error or that contribution in the sum here can be computed here with the difference of the true value and the predicted value with all points, but with a factor here that depends on basically the problem. So the empirical error will just sum the numerator here. We said it's bad. The nice thing is to compute this, but roughly speaking, you would need n polynomials training. And my equation here says no. To compute this, which is the right things to compute, you need just, as before, a single polynomial expansion, but what you compute in the end is this a bit more complex equation where the matrix that is used from the least square minimization appears in this term hi here. Okay? So as a summary, as soon as you have selected, maybe I can go there, as soon as you have your experimental design, you have truncated a basis somehow. I will comment this in a second. Basically, you solve with least square, you get your coefficients, and as a direct post-processing with this equation, you also get a good estimate of the validation error of the model without wasting any points for validation. Okay? Now, commenting on this, for this to work with the standard least square, maybe you also know this, if you have a least square problem with a number of unknowns, you need more points than the number of unknowns. Otherwise, the problem is underdetermined, and then you don't have a unique solution. But if more than that, if you want to be accurate, you just don't need just more points, or at least as much, but you need typically twice as much, or way much more points than the number of unknowns, number of unknown coefficient. Okay? So we assume for now that we do this, well, this condition holds, that is the size of the experimental design is at least, let's say, twice bigger than whatever truncated series we consider. Now with the error estimation, basically, we have a fully adaptive, we can define a fully adaptive procedure, because what I would define is not to ask myself, should I consider polynomials of degree 2 or 3 or 4, how to decide? No, what I decide is I want this error to be less than 10 to the minus 3, and then I would test different expansions, and for each of them compute the error, which is direct post-processing, until I get the best one. Okay, and again here this kind of thing usually I teach at ETH, and it takes several weeks, so I cannot give you all details, but basically if you have a lot of information, increasing the number of polynomials, the quality, so the error decreases at some point, and then it starts again to increase. It increases when you have such a number of polynomial coefficients to compute that it comes close to the number of points, that then you tend to overfitting. So the error as function of the degree, which corresponds also to the function of the total number of unknowns, is like this. So at the beginning, going from degree 1 to 2 to 3, usually you get a better error, but going to degree 10, you may think, okay, it's degree 10 is better. No, it's not better because of the overfitting procedure, and we can avoid this because that error estimation gives this curve where you find the minimal error, and then you can select between all the models. Okay, so this way we start having a procedure where we have a clear error estimation, that is the mean square thing, and we have a way to compare different polynomial chaos on a very rigorous way with this mean square error.
I'm sorry, the question
Yep.
about notation. Can you please go back one more? And one more, please. Yes, here. Where you PC/E, you subtract index, one element.
You don't use one point. It's exactly this here.
It's a point or it's index?
No, it's point. You don't use that point in the analysis, okay? But in practice, you don't need to do this because to compute the error that would be defined properly with this procedure, actually you just compute once a polynomial with all points, and you use a fancy equation that is not just the mean square on the points, but kind of weighted by what is needed so that you mimic the problem of leave one out. It's something that comes from the least square matrix, the A matrix that I defined at the beginning. It's the diagonal term of A transform A inverse. That here is the regression matrix. Multiply left and right by this. I mean, this is purely algebraic derivations. Okay, and this is basically now our first algorithm. And that's where I come back to your question. The only input is how much I can afford. So if you come with a problem and tell me, well, okay, in a reasonable way, a few days maybe, or 2 days, because I want results soon, I can start with 50 points. Okay, let's start with 50 points. I don't have more than the only input of the algorithm, which is, in this one is very basic, we go more complex later, is how much you can afford. How much you want to compute times the original model to start something. And what you get out of this is an expansion, the best one you can get with this amount of data, and the associated error. Okay? Yeah?
Could we, I mean, now we have this adaptive basis building by using the minimal error, right? And we increase the basis. Could we also do something like a sparse regression kind of thing? Because we're always building more coefficients, right? And it just would be, maybe the linear coefficients are not useful at all, right? Only the higher orders matter.
Next section. Okay, before doing this, I come back to, again, this you have seen already, what is called the curse of dimensionality. Again, if you take, as you said, all those coefficients, which are represented here, each point corresponds to a polynomial, and then it has a coefficient, okay? This number of coefficients, when the dimensionality, which here is 2 and could be 10, 20 or more, and the degree, which is in this direction, how many lines you have, if you increase this a bit, you get huge numbers. So I put a table just for fun. It's very common that we would need 50 input parameters and typically at least polynomial of degree 5 or a bit more. You're already, with what I've said so far, in the range of millions to tens of millions of coefficients to compute. And if you remember this thumb rule that you should have at least twice more data points, then this becomes useless. Then just do Monte Carlo simulation and becomes useless. Okay, so this is now not enough. It's okay if we are in this domain, like 2, 3, 5 parameters. Okay, we could do just this and that's okay. If we want to address high dimensional problems and non-linearities where you need high degree polynomials, we need something more. And that's where sparsity comes into play. I think there was also questions about the coefficients before. I give you here an example, which is a pure mathematical function, but it's very, explanatory example, let's say. So it's a function of 3 variables, and variables are uniform between -pi and pi, okay? It's only 3 variables, so I want to do a piece expansion. I can afford a large degree because I want to be accurate, say degree 12. So 3 variables and degree 12, you put these 3 and 12 here, you get 455 coefficients. Okay, manageable, especially because now evaluating the model here is analytical, so it's inexpensive. Suppose that I use really a huge number of experimental design points to compute very accurately these 455 coefficients. Maybe I put 10,000 points in my experimental design, so really I'm almost sure that they are very close, this 455 to the true value. And then I plot here the magnitude of those, let's say, exact coefficients as a function of their index from 0, 1 to 455. Maybe you can make this bigger here. Yeah, so what you see is the following. And there are colors here. So this is normalized with the 0 coefficient, which is the mean value of this function. And this is a log scale. And what you see is that, and then there are colors. You see that the first order are blue, second order polynomials red, and so on. You see two things. First of all, you see that out of 450, there are maybe 20 that are above 10 to the minus 5. And remember, a coefficient which is 10 to the minus 5 relative to the mean, when you put it into the computation of the variance, would be 10 to the minus 10 in the variance. So any coefficient here, even if this is exactly the true value, contributes to 10 to the minus 16 to the variance. Who cares? Okay. So you see that out of 455, you really need 20 to be accurate. But the problem is that those 20 have different degrees. You have blue, red, yellow, but you also have many other non-colored coefficients which correspond to very high degree. They are important to get accuracy, but they are very high degree. And in contrast, you have a lot of first and second and third order coefficients that are, yeah, almost 10 to the minus 6. Okay? So, question, would it be possible not to compute this 455, but just the relevant 21s? And that's exactly the goal of sparse expansions. Find algorithms that will select from the data which polynomial and which coefficients should be computed, and only those ones. Okay? And what we observe here is very generic. Again, it's like a bit, not even extreme, but like very standard, let's say, situation where a lot of coefficients are almost 0, even if you were able to compute them exactly. So that comes, generally speaking, from something called sparsity of effect principle. There is a fancy name called Occam's razor. Maybe you have heard this sometimes, because also in machine learning community, people like to refer to these fancy names. That principle basically says that if you have different models, very often the best one is the simplest one in terms of explanatory things. So back to our physics-based models, if you parameterize some geophysics, whatever flow into the soil using the porosity, what's the other? Permeability, porosity, and a few other terms. Why people did derive equations with those parameters? Because, well, that's the physical parameters that explain the phenomenon. And the thing is that if the equations are written with those parameters, then these would be our inputs. Polynomials in those input parameters, basically with lower order terms, that is linear terms, quadratic, maybe a few higher order, will basically give a very good accuracy. And what means this sparsity of effect principle also is that not only it's typically low degree, but it's also what we call low ranks. That is, again, back to the Sobol decomposition that you have seen, most of the information is in the univariate effects. And then you may have sometimes bivariate effects, but for sure, all these high order interaction terms, they are 0 in practice, most of them. Okay, so we define a new quantity here, which is for a given polynomial, what we call the rank. It's basically, well, this equation says the sum or the number of non-zero terms in the degree of the polynomial. So again, imagine m is equal to 10. You would have integers that are the degree in each dimension of the polynomials. And this rank is basically the sum of the non-zero. So what does it mean? If you have a rank 1, it means that it's a polynomial that in practice depends only on a single variable out of the possible, let's say 5 here in this simple example. Rank 2, out of the possible polynomials which may depend on the 5 variables, a rank 2 means it depends actually on just on 2 of those variables because it's 0 degree in the 3 other ones, okay? And again, this principle here, when you analyze on many problems which are the big coefficients, the ones that I've plotted, they always, most always, corresponds to these low ranks, that is to the polynomials that depends only on 1 input or 2 inputs, but almost never on polynomials that would depend on 5 different inputs. Now, if I remember this grid plot which shows which shows the polynomials with a green with a blue point in 2D, same now in 3D. The rank 1 polynomials in this problem where we would have 3 dimensions would be polynomials that depend on a single variable, so only on x1, only on x2, or only on x3. If I put the degrees, that would be polynomials like degree of x1, 0, 0, or 0 degree of x2, 0, or you understand. If I plot these same points, these correspond on the grid to these points on the axis, like 2 coordinates are 0 and 1 is non-zero. The rank 2 would be polynomials for which out of the 3 degrees, 1 is 0 and the 2 others are non-zero. So in this representation, they are on the planes, okay? And the real rank 3, so the polynomials that really depends on 3 different variables with a power in each of them, would be somewhere in, not on the lines, or not on the axis, not on the plane, okay? So this will be this view here. Now try to imagine the same figure in dimension 10 or 20. In dimension 20, you just have 20 axes, but that's it. It's just 20 divided by 3 bigger. Here, here it's quadratic, but for any other interaction more than 2, you have a huge number of terms which was in the table, these hundreds of millions. They come for the higher interaction, or high rank, let's say, it's the same. And when you solve problems and you compute them, those are the ones where the coefficients are 0. So you want basically not to compute them. This comes to your question, how to a priori then say, I would like not to compute them. So not start from this truncation by degree, which explodes with the degree, but make sure that I have all the blue points. Where are they? All the blue points, so I can have in each dimension as polynomials of each single variable, maybe up to degree 10, maybe some interaction, but for sure, really little interaction, really little orange polynomials, okay? So one way is to truncate by the rank. You can say, okay, I have a huge basis. Let's just consider only the rank 1 or 2, and all the others I don't put in my expansion. So that's another way to truncate. This is okay, but in an adaptive way, this may not work because here that would be, let's say, graphically considering only the blue and the green polynomials. And if you increase the degree, then you have more blue points, more green points, but you have never any orange polynomials that are of interaction at least 3. And maybe some terms are needed. So if you truncate by rank, like fully, increasing the degrees will not cover the full space. So it will not be dense in the thing, in the full thing. We define another way to do this, which has the same effect, but now if you increase the degree, you will always get as many interactions as needed. It's this so-called Q norm, where basically, if you plot it, instead of having these lines here that we had to define what are the points that you add when you increase the degree, you get something that looks like an hyperbola here. So if I go to degree 10 with this, I would have for x1 and x2 or x3 really up to degree 10, but very few polynomials represented by these few points here that have some interaction. And this you can monitor with this Q value, okay? If you go to Q very close to 0, like 0, basically you get what we call an additive model, that is a polynomial that contains only univariate polynomials in each term. So that would be the first part of the Sobol expansion, basically. Okay? And no interaction. Q equals 0 means you assume there is no interaction. Q equal 1 is the standard thing we have seen before. So if you select something in between, a priori you say, you still select the degree, so you still say, I would like to go up to a certain degree because I think there is nonlinearity. But a priori, I think that there is little interaction, so I will a priori, select only those points to compute instead of all those points. And now in terms of number, I'm not sure you see very well this graph here. Again, it's a bit big. Okay. If you take the standard truncation by degree with polynomial of degree 3, 5, 7 and increasing the number of inputs, let's say take 50. That's what we have seen in the table before. Degree 50 input parameters and degree 7, you're close to hundreds of millions of polynomials, 10 to the 8. Okay? So it's not manageable. Just by this trick of changing this Q, you immediately get a truncated set that still has very high degree polynomial in each variable, but far less interaction term, and now you're down to a few hundred, maybe 1,000 unknowns of the problems. So that is the smart way to, a priori, independently on the problem, not consider millions of polynomial terms, but be always in the range of a few thousands, maybe. Okay, that's another vision. And that's just, again, an a priori thing. But if I come back to this scheme that we have seen before, even in that case, it does not solve the problem, because you see, I have, even if instead of computing 455, I would now maybe compute only 100, still I need high degree terms to be accurate. And again, out of these Q norm truncated things, again, many polynomials and corresponding coefficients would be 0. So the ultimate thing is to compute only the non-zero term, okay? Only those ones. And that, again, we did not invent it. That can be done by basically changing our means least square problem into a penalized least square where we want somehow to have a limited number of coefficients. So the real thing, which is what is the best, so the minimal error for a given number of terms, but also with a limited number of terms, would be to penalize with the number of polynomials you want to have. So put here a zero norm, which is really the number of polynomials. This is not well posed, but well, this is like a combinatorial problem to test all possible expansions that would have exactly 1, 2, 3, 4, 5 terms, and so on. But if you put the one norm here, so the regularization term here with the one norm, the sum of the absolute values, then you enter the world of basically sparse solvers and selection models that is also very well known in statistics for 20 years. And you have tons of algorithms that solve this problem. That is, that solve the problem of being good in the least square, but just with a few terms out of many possible terms and not taking all of them. One of the first algorithms to do this, 890s, is so-called lasso, which is one way of solving this penalized least square problem with the one norm. It's called lasso because basically you pick some of the terms, but not all of them. 2004, there was another very efficient algorithm called least angle regression, again, that solves somehow a similar thing, so allows to compute expansions with not all the full set of coefficients, but just the most important one, meaning the largest coefficient. Remember always that the coefficients have a meaning. We have an orthonormal basis. So when I say here it's a big one and here it's a small coefficient, it means something because the magnitude of the coefficient is related, I mean, they are comparable in magnitude. So something can be small, something can be big. So the least angle regression, I did not put the details. If you're interested, just contact me. I have like extended version of all these slides where there are far more details. But basically, this least angle regression will do the following. It will say, okay, you have a big candidate set of possible polynomials. You don't want to compute all of them. If you started with just one, which one would it be? So back here, let's do this in 3D. This, we enter the world of greedy algorithms. Suppose that my solution is here with the 3 coordinates, this one here, and this one here. So here, if you had the choice of choosing just one polynomial to approximate this, where the 3 coordinates are 1, 2, and 3, obviously you take this one because it's the biggest. So if you do this, that is, you take from, where is it? From here, and you take what is basically the largest projection, and then you come up here, and then the residual is basically this thing here. Well, it's in 3D, so this thing here, and then you start again. Doing this, it's called orthogonal matching pursuit. It's a greedy algorithm that basically, at each step, try to get what would be the next biggest coordinate, disregarding what has been computed so far. It's one way, works quite well. This one is, let's say, one step better. It does not do exactly this, but still, in a greedy way, it will find one by one the directions, so meaning the polynomials that have the largest coefficient. And so you increase, this way you increase the basis from 1, 2, 3, 4, and so on. For each of them, computing the coefficients, again, you have few coefficients. So it's a matter of least square, which is very simple because you have few coefficients. And for each expansion with 1, 2, 3, 4, 20 coefficients, you have the least square, you have the error that I mentioned before, this leave one out. So again, you can compare all of them. All this is extremely fast. It takes less than a second with standard problems. So you build basically a set, not just now anymore an expansion, you only define a big candidate basis, and the solver automatically will find not just one PC expansion, but a full sequence of those, compute the error, find the best one out of this. And it can be maybe that it has psi1, psi32, psi128. It will find directly the right coefficients. Okay? So this is basically what I just said is the inner loop here. Oh, I have a pointer here. So basically, for a given candidate basis that is defined by how you truncate it, that would be Q, and what is the max degree, that would be P. Find out what is the optimal sub-basis, sparse basis out of this, compute the coefficients, and then return me the error that I can estimate. And this now, again, very easily, I can test starting with the candidate basis with just polynomials of degree 3, 4, 5, 6, and so on, and different Q norms, because a priori for a given problem, I don't know where I should stop. This is not anymore a question, because I just do a for loop on this, and each combination returns an error, and I do the minimal of all this error. And again, testing here 10 different degrees and 5 different Qs on standard problems, that takes 10 seconds on a good implementation. So in the end, we start, again, with the input, how much you want to pay, and you have a fully adaptive algorithms that out of this data will extract the best possible sparse basis with the coefficients, with the estimation of error, with the Sobol indices for free, with the PDF and everything. So if you're, well, maybe questions. Main question is, why don't people only use this? That's my main question, because no, there are problems, it's not so easy. I mean, this morning Ryan presented hyperbolic equations with steep fronts. Okay, that will not work directly. Sometimes you need a bit more than that. But I mean, in really many practical problems it works. You had a question, yeah?
So how does it compare, like for GPs they have a problem with extrapolation, right? The Gaussian processes. So does the same thing applies here?
That's the same thing, but that's not a question. Sorry. You should never extrapolate anything when you do surrogate. Basically, you have a model that's supposed to be good. And it's also supposed to be good on a certain range of the input parameters. And the question is just, okay, on this range, I'd like to have something 1,000,000 times faster. That is not too bad. But I don't want to estimate the model here. I have no information here to fit my surrogates. So why would I fit it here and evaluate it here? This is a dummy way of doing it. It's a good question because people still do it in many papers. But you should never do this. You should learn a model with data, and also in machine learning, and use it with the similar data. You cannot learn it here and then use it here. There's no way this extrapolation works. Or if it works, it's really by chance. But yeah, never do this. So
you need some kind of information regarding your parameters to start with them, to set the bounds.
yeah, but that's the whole point of this. Set the bounds, define the input distribution, somehow define the basis polynomial. So you cannot do this in the blue. I mean, you have to start somewhere. And the basic starting somewhere when, let's say, experimenting what's going on out of a model is to really yourself or talking with people who know the physics or experimentalists, whatever, and say, okay, what is a realistic range of this? If you have really no clue, then you should somehow find information or take a very wide range. But in any case, even if you take a very wide range, whatever you surrogate should be within this range, not extrapolating outside. Okay?
Can you please go back to the algorithm for a second?
Yeah.
So in this case, how do we tune the parameter Q?
It's not tuned, it's selected. It's a discrete selection. I take degree, then it's also, I mean, given the dimensionality and the number of points, if you send me data, I know empirically after doing hundreds, not hundreds, but dozens certainly, I know which P and Q should be realistic. But typically Q would take, let's say, 3, 4 different values. P we take to start with from, let's say, 3 to 10. And that's just 30 analysis. And so there is no, I mean, it's brute force. On that level, it's brute force. Because each inner loop takes a second or 2 seconds. So, yeah.
Would you change if I have not a random scalar random variable, but random process or random field?
In the output, you mean, or in the input? Input.
Let's say porosity, permeability, random
Field. Yeah, so then that's what we discussed also this morning. Then you need, I mean, it's an infinite dimensional object, so you need to discretize it to do any numerics. So then you, well, in standard techniques, Karhunen-Loewe expansions, things like that, which allow to represent the input field into a finite sum of variables times certain modes, certain spatial shapes. And maybe you need 10 or 20 or 100, and then you're back to a problem with 100 parameters, which are the coefficients of the KL expansion.
So, but still you...
I do the same, yeah. Yeah, we have tons of examples, yeah. And why it works well with those kind of sparse approach compared again to sparse grid approach, if you have 100 dimension after discretizing the inputs, so 100 terms in this random field inputs, you can do PC expansion with 100 inputs, but then you come to a very large number of terms, so you stick to low degree probably. Here, back to the idea of sensitivity analysis, you may need 100 inputs to get certain accuracy of the input discretization. Typically, you know the thing, you have these eigenvalues, the total trace, you explain 99%, something like that. So maybe you need, I don't know, 200. But this does not mean that now the output depends on the 200s. And again, because of sensitivity analysis, you can check it by sensitivity, but because of the usual physics, usually the physics filter out the modes. So if you take a problem where you have a random field of porosity, you put some flow here and you get some output flow, this output flow somehow is a scalar quantity, will kind of average what's going on in this random field of permeability. So maybe because of your assumptions, you define very small fluctuations at very small scale in the input field, but those usually will not play any role on an average quantity, which is the output flow. So that translates into, okay, I need many x's to properly discretize the input in terms of accuracy of the input. But in fact, out of 100 parameters, maybe only the first 3 ones play a role to explain the output flow. And so if you don't have an algorithm that automatically found the 3 important ones, the 3 first modes typically, well, you have to work with 100 dimension. With this kind of thing, you give the 100 dimensions, but if the problem, the output of interest, only depends on the 3, or 5, or 10, it will automatically find them. And so that's why we can do random field stuff with this with no problem. Okay? So if I mentioned at least 2 solvers, OMP, orthogonal matching pursuit, least angle regression, and there are tons of them. So at some point, seeing more and more paper with new solvers claiming this and that, we decided to, well, compare them because nobody takes the time to compare them. They provide a new solver, then it gives 2 examples where it's slightly better than another solver, and that's it, and it's a good paper. So we have 2 papers 2 years ago, last year, where we really took, I don't remember, but close to 10 different solvers, 11 different problems of all kinds of dimensionality, different sampling scheme, everything that you can vary in what I have explained. And then we compared exhaustively, trying to make conclusions. So are there solvers that are systematically better than others or systematically worse? Are there sampling schemes to define the experimental design that are always better, and so on? And yeah, we compared this. This was a huge work from my former PhD student, Nora. And yes, there are conclusions. So conclusions are like least angle regression, that was the first one we used 12 years ago, 13 years ago, actually is not bad. In average, it's okay. It's quite good. Sparse solver. How to compute the sparse expansion, how to find the sparse terms in an expansion. That problem has maybe 20 different types of solvers. So least angle regression is not bad. There is something recent called subspace pursuit, not from us, that works very well. So that would be now our default thing because obviously it has shown very good. In other setups where you have very little data, coming back to your question, like starting with 20 points, there are Bayesian compressive, BCS, Bayesian compressive sensing solvers that put a Bayesian flavor to this. And with this Bayesian, you kind of put some prior information on the coefficients. So with little data, you already get something. So the range of, let's say, high or big dimensions, but very little data, like 20 points and 20 dimensions, that's, well, not much. That happens to be a Bayesian solver that is always better than anything else. So we have all kinds of conclusions also on the sampling scheme. And so this basically allows to, well, you start with a problem, you have no clue about all these things. I will share my slides anyway. Then basically you should get recommendation how to start with. And there are several software packages that then implement those things. Our UQLab, but there are others. So at least you know how to use it to basically have some expert knowledge how to best use it by default. Okay. Yeah, I think I will go now to, again, 2 applications. One is analytical, very simple, because then I can do all kinds of simulation and show you the power of things. And then a real one where we have a big solver, a big computational model, many variables, not many points, a real case. So the first one is exactly the one I mentioned to show the surfaces. It's this bearing capacity here as a function of the properties of the soil, so the maximal pressure before the soil collapsed around. It's basically this simple equation with just 3 terms depending on the phi, friction angle of the soil, and the C coefficient somewhere here. So very simple, I can do everything. I put some realistic distributions. Again, here we don't do just pure mathematics. I mean, it's a physical problem of geotechnics. So we know that typically friction angle and cohesion based on many data, experimental data, or on-site data, follows usually log normal distribution, and these are realistic parameters for this kind of problem. That's another point. Never extrapolate, never use models here that you put anything and see what happens. I mean, if you do physics, and in geophysics there is physics, you should put values for your distribution, for your ranges, that make sense. Don't try to do in the blue a huge surrogate or sensitivity varying something in a huge range that makes no physical sense. You will get bullshit, and you will also basically make no conclusions out of it. So really the step that says, how do I choose this here, what's in this table, has no interest in the terms of surrogate modeling theory, but for practical use, it's as important as whatever I use afterwards. If you put here something that is completely irrelevant, you get something completely irrelevant at the end. So this is important. Okay, so I start to, now you see here, my model is analytical, so I can use huge Monte Carlo simulation to do whatever I want. Propagation, density, Sobol indices, I can all do with Monte Carlo, and then I can do with the standard sparse PC. Okay, so let's start with 100 points, which is in 2D already big. I mean, it's a lot. So I just say, this is my equation, this is my 100 points, just do something, and again, in probably 3 seconds, that's what I get out of my software. It says, well, with the data you gave me, you have 5 inputs. Basically, I tested different degrees, different Q norms, but the best I guess is taking maximal degree 3, and then with the solver, out of all possible polynomials of degree 4. In fact, there will be 70 such polynomials. The best sparse basis has only 33 coefficients that are given or computed, and the error is 10 to the minus 5. You see already 10 to the minus 5. It's way too much from an engineering point or practical point of view. People are usually happy with 10% error, so like 10 to the minus 5, way too accurate. Anyway, so now you, with these 100 evaluations, you can do 2 things. You can plot the distributions of the PC expansion fitted with 100 points, and you can sample a million times, million times, let's say, the original true model, because it's analytical in that case, and compare the PDF. I'm not sure you see any difference. In fact, there is a difference here in that corner. That's the only difference you can visually see. One costs million or 100,000, one costs 100. You can also do what is called validation plot, where now here it's a kind of, again, average. It's like the mean square error. It's like an average accuracy that you see here. But you could do point by point. This requires that you have a validation set. So this kind of thing I can do only in the case where I want to prove people that PC is worth it. So when I can really do an independent validation with the true model, because my true model of the foundation is analytical. So I can really take, again, this 1,000 or 10,000, and now point by point predict the true value and the PC expansion value. So if it was perfect, that would be like just a 1-1 line, okay? So you see here, that plot tells you, oh, it's quite good, but it's not good for the very small values. And that could be an issue because usually we are interested in the low values, extreme low values. So it tells you where it's not good. So if we do this with 30 points from the distribution, it's still acceptable. Now from the 1-to-1 value, you may get a 1-to-1 value error that is here, 10% or 20%. So maybe that's not acceptable. But just with 200 points, now there is absolutely no difference on the obtained distribution. And in the 1-1 here, I mean, apart from a few points here, it's also almost perfect. And the mean square error is not reported, but it's probably 10 to the minus 8, okay? Okay, it's a very simple problem, but just to give you orders of magnitude. I can compute the moment. So you remember the mean and the variance. So this would be what I can do from Monte Carlo simulation. Remember, you take big samples, then the mean should be more and more accurate. And it looks like it's this number here and this standard deviation. I did not show how, but again, trust me, each time you do a Monte Carlo simulation to compute the mean or the variance or whatever, you can easily get not just the value, but a so-called confidence interval, because basically, well, there are different ways to do this, bootstrapping or other methods. So this emulates the fact that if I take a sample of 100 points to get this value, if your neighbor takes another 100 sample, he will not get the same value. So instead of one value here, I should give the range that is the pure statistical uncertainty, because I used only 100 points. Okay, and this range, if now I go to 1,000, 1,000,000, collapse to 0. Okay, so you see here, if I take 1,000,000 points, still this confidence interval, I mean, it's not, you have 3 digits that are okay, but the 4th digit changes. Okay, so you are up to maybe 0.1%, and same for the variance. Now, I can do the same with PC expansion. I take just 100 points, but instead of doing this once, I take several samples of 100 points, and I do different PC expansions, so this will be different coefficients, and I will get different means, different variance by summing the square. Okay? And I can do the same, this confidence interval. So that's what I get here. The mean here and the variance, basically, they are similar to what we get between 100,000 and 1,000,000. And if I want to get a range that is so small here, for the mean and the standard deviation, I need to go at least to 1,000,000 points. But that has costed me 100 points. So not only this is an excellent prediction that, in fact, I think that's the true value. So even with 1,000,000 points, the standard deviation estimation is probably more wrong here than what we get here. If I use 10 millions, probably I come to this number. But also the variability, because you would claim, okay, but if you have only 20 points, that's nothing. So the variability, if now I redo the full thing with 20 other points, maybe I get something completely different. No, you get something very, very close, because all this procedure, well, has a lot of things that make it stable much more than a crude Monte Carlo simulation. So again, in summary, you get as accurate results with here 100 compared to 100,000 or million, and the statistical variability that comes out of the selection of the random points is also same order of magnitude as if you add 3 orders of magnitude more points. I can do the same with Sobol indices. So then here it's about what proportion of the variance in percentage you explain by each parameter. And that problem here is really trivial, because most of the variability comes from the friction angle, because you have all this exponential phi somewhere. So, okay, it's very sensitive to phi and almost not sensitive to anything else. But, okay, that's also quite standard. You can compute, I did not show how, but you can compute Sobol indices by pure Monte Carlo and again get confidence intervals. That's same story. And if you want to, let's say, be accurate to the second digit, so like 96% here and 1.5% for the others, you see that you need for each index 1,000,000 points, samples, and as I have, in fact, something missing. I have 5 variables, or 4 variables. I need this many times, so in total I would need 6 million points. Now I redo PC expansion with my same 100 points. I do the PC, I compute the Sobol indices from the PC, that's analytical, and I do this a few times, again to have ranges to see the stability versus the choice of these random points. And again, you see that this here is even better in terms of precision, that is, it's 96.3% plus minus 0.01%. It's better with 100 points than with 6 million here. These ranges, these numbers on these simple problems, that's what we get on any kind of problem, more or less, okay? Orders of magnitude, better accuracy for a given sample size, or let's say 3 orders of magnitude less samples and less computational cost for the same accuracy. Okay? Now, to conclude this, and I don't know how much time I will spend on Gaussian process afterwards, this is a real case. So this has to do with actually geology or geophysics. It's about nuclear waste repository in France, where there are models that basically compute if you would put some, if you will probably put some nuclear waste here, like 400 meters, where is it? 400 meters below the surface in a very impermeable layer. Well, at some point in many decades and centuries, there could be leaks in those waste nuclear packets, and these leaks could go through the surface and through the layers and go up to the surface, okay? So what is the average time needed to get some contaminated things go back to the surface? That's my quantity of interest. And this is the kind of model, I have no clue of the details, but colleagues from Neuchâtel University did the models a few years ago. This is a model where it's a 2D geophysics. In each layer, you have 15 layers. In each layer, you have 5 parameters, plus boundary conditions. Well, in total, this is a problem where you could identify 78 parameters in terms of porosity, conductivity, also, don't remember the name, but there is a tensor of tortuosity or something like that. Things that really in each layer give you what are the terms you put in the flow equations, basically. Question is, okay, how sensitive is this time, let's say safety time of the storage in terms of thousands of years before something would escape to the surface? What is it sensitive to? We did here, because we did not know back then how complex it was. So 78 parameters was probably one of the biggest things we did back in 2016. And we asked our colleagues 2,000 runs, 2,000 points. So it took them a month or more. And then we used the 2,000 points in different ways to fit PC expansions and then compute Sobol indices. So long story short, in the end, we realized that, first of all, as always, out of 78 parameters, basically you have 5 parameters that are basically conductivity on just 5 specific layers that really plays a role. Anything else, you could just put whatever guess you want. That does not change at all the safety analysis of this thing. And to get those numbers properly, in fact, we don't need 2,000 runs. We took then subsampled the 2,000 to 1,500 and up to 200. And already with 200, you get the same results. Why is it the case? Because in principle, you should have polynomials that depends on 78 different variables. Why is it the case? Because the important terms are again polynomials that depends on each single conductivity separately and maybe pairs of conductivity of 5 layers out of 15, and that's it. Anything else plays no role in the safety analysis. Okay, so we got here the accuracy, it's not written, but it's a real problem. High dimensionality, small data, 200, we get 5% leave one out error. So you may imagine 5% is not very good. Indeed, for, let's say, if I want to predict point by point, you give me 78 parameters, I give you the number of years before a problem arises. On this one-to-one, I may be wrong for 10, 15%, certainly. But for the sensitivity analysis, this 5% is good enough to get very good stability of the sensitivity indices. Okay, so again, here we don't talk about theory. The theory and the convergence, everything is well known, and there are also proofs of all kinds of convergence in certain setups. But now when we talk practical problems, it's very complex, costs a lot of time, and I can afford maybe 200. So that's the everyday life of scientists, and you see that we can solve this type of complex problems. Yeah.
So related to the variance space, this variance space, for example, for nuclear waste disposal, like it's actually literally related to the extreme events. So for example, like your TOIs should have like an extreme distributions. So is it really enough just to do sensitive analysis?
Very good question. No, you're right. So here we did what I just presented. From another perspective, what would be interesting is look at the extreme values and maybe extreme low values of this number of years. And then we can formulate what I will call in the next slide, if I present them, a reliability problem. So you have a threshold. You want to compute the probability of this extreme event in one or the other extremity, let's say. And you can do sensitivity related to these extremes. And that would be, in your case, your question. And I agree, would be more relevant in that case. It's not what we did here. That was a general. But here, what you answer as a question is, people in France, as far as I know, they investigated, like now for 20 years, this site in Bure, because they have started already a lab here in this layer, and they do all kinds of analysis. And as far as I know, they really investigated the soil properties of each layer, the same accuracy, the same number of samples in each layer, and same number of millions of euros in each layer, or in total, to really have the best knowledge of each layer. This analysis shows that apart that layer, the one below and the two above, the others, even if you know the conductivity is wrong by 1 or 2 orders of magnitude, does not change at all the results in this safety analysis. So, okay, you need some numbers that are not completely wrong, so you need maybe the mean values of those ranges. But having 50 samples in each layer to get this range is probably useless. So that is the kind of thing you can get. Of course, a posteriori, it's not so useful because they did the data, they spent the money, but this is the kind of thing you can investigate a priori before doing too much experimental or on-site investigations. Okay, so my conclusion is that everything that I presented you can find in our software. So Ryan mentioned it, it's called UQLab. It's a software developed in MATLAB, so it's basically a MATLAB toolbox. If you don't like MATLAB or don't use it, we have an online cloud version that is fully Python-based, so you do exactly the same. It's not a Python package in the sense that you will not find all this algorithm written in Python. What you get is an interface that basically allows you to run the MATLAB version of UQLab in a transparent way using Python syntax. So you cannot get into, if you want to get into the details of the algorithm, you have to read into, because it's open source, you have to read into the MATLAB version. But if you use Python, you can use exactly 90% of the features from a Python environment. And the mechanics is that you basically don't do anything locally because there is no local Python software. You connect to a distant server that does all the cloud computing for you and go back and forth. You send requests and analysis like compute suball indices or compute the moments or probability of failure, plot me the distribution, whatever. And this is executed with the compiled version on a server for you, so it even saves memory and things on your own machine, and then you can enjoy the results. So we started these developments now close to 10 years ago. We have more than 6,000 users all over the world, and it grows by at least 1,000 every year now. And yeah, as I said, it's MATLAB or Python, just use one you want. And also this is important. At some point we had a lot of users, so a lot of requests. So we stopped replying one by one. We made a forum to do this. And it started as a forum to how to solve this UQLab problem, let's say. But now it's bigger. We call this UQ World, and it's really a general purpose forum for questions on uncertainty quantification. Even if you use other packages, other software, basically you want to do this, and you ask people on the forum, did anybody already have this kind of weird uncertainty quantification problem? And we have 600 active users, so you get replies either from us or for anybody using the forum. It's quite active. And yeah, it's also a good way, as a beginner with those techniques, fancy surrogate modeling techniques or other things, if you're not sure how to do something, you can ask some help. And then important thing, also if you don't want to use the software, if you go to the website and click on documentation, you get something like 1,300 pages of documentation of the software, where most of it explains you how to do things, not just how to use the software, but what is sensitivity analysis if you have never seen it? What is polynomial chaos if you have never seen it? What is Bayesian calibration, RBD, whatever is provided? Those manuals are not the usual software docstring documentation. They are written by us, and this is what takes us the most of the time. It's not the development. It's really putting a lot of examples. There are probably 100 of examples now, and writing a proper documentation so that people really can learn the thing. So yeah, if you want, enjoy it. Yep.
I have a question. What if the parameters that you're starting with, the set of parameters that you have the prior on, depends also on time? So they evolve
in time, yeah. Okay, it's not in my slide here. So there are different cases. Again, it can be something that varies smoothly in time. So you have a time series, but I don't know, some nice dynamics. And when you vary parameters, it's the same dynamics, but a bit shifted, okay? In that case, again, principal component analysis. So you represent those curves with a few modes and a few parameters, and those few parameters will be your few input parameters, okay? Now, completely different setup that we have in civil engineering, earthquake engineering. You have a building that you simulate with some finite elements, and the excitation is this very, accelerograms that you probably have seen somewhere. This is completely unstructured, and if I take another accelerogram, then it's completely different. And if I change the properties of the building, maybe I change the main eigenfrequency, and then suddenly for one signal, it starts oscillating like crazy because there is a resonance, whereas a very close other signal is completely different. So there you need more than just what I said today. So to capture the fancy dynamics, basically we put this together with autoregressive models, nonlinear autoregressive models. Because typically when you have transient inputs, very often you have transient outputs as well. So yeah, that requires to put together this with some, again, intuitively it's something that is the right representation of the dynamics in time, okay? Let's consider the output, where the output would be like a time series or space something. If there is a lot of smooth variability, as I said, you could imagine doing a PC expansion for each time instant or each point in space in the output. If it varies not too much, it will work. It will just be costly because if you have 1,000 time instance, then it takes time. And that's where, again, compressing by principal component works very well. You get the same accuracy, almost, and just with a few expansions. If the output is really like oscillating like crazy, let's say, we have this for earthquake, we have this now for wind turbine simulations that give you the blades behavior under wind field, incoming wind field. You need more, so typically these NARCS models. Another problem, don't know if anybody is interested, but many people work in the frequency domain for dynamics, and then you have some kind of vibrating system, and in the frequency domain, you have this so-called frequency response curve that shows you the amplitude of, let's say, some vibration or displacement as a function of, let's say, the impulse frequency, okay? And that's where you see the resonance. So you have this kind of curve where you have really sharp peaks, which corresponds to the resonance of the system, and anti-resonances sometimes. And again, think in terms of uncertainty, then you have such curves that basically are now peaks, one's left, one's right, one's small, one's bigger. So it's a bit fuzzy. If you try to do PC at each frequency, no way, again. So you have to find a better representation of this thing. And then again, here there are techniques that is called frequency warping. Okay, if you want details, I can tell you. But all this is, let's say, somehow pre or post processing the data so that at some point you come back to a limited number of parameters input and outputs where you can apply this. But between the original problem and this, sometimes indeed there is pre or post-processing with compression or with representation on temporal basis or other stuff. Okay? Yeah?
Do the parameters have to be independent of one another, or what happens if there is some
No. I explain it mainly with independent. If not, to use polynomial chaos, as I said, you have to define how is this dependence, and once it's defined, again, that's probability tools, independent of this, that allows to map a dependent random vector as a function of independent variables of another type. So you would do this, and instead of expanding m of x, if I call t this transform between dependent and independent or auxiliary independent variable, instead of expand m of x, you expand m of t of psi, let's say. But that's it. This is analytical, can be complex, but it's analytical. Typically with copula is one thing. There are fancy ways called Nataf transform. There are different ways. But then in the end, practically with polynomials, you work with independent variables. Even if they are not the original physical variables, you do, again, a kind of pre-processing before applying this. Yeah. Which brings to the point that, and opens a wide question of what is sensitivity with dependent parameters, which you did not ask the question, but I can give you an answer anyway. If you do this, then you would have a piece expansion on these auxiliary variables. So you could do Sobol indices on those variables, but those are not the physical variables because you have this fancy mixing that uncorrelated the things. And, well, there is no unique way and there is no agreed way of how to define sensitivity, whatever measure, if you have dependence, because there is always a mix between the statistical dependence of the inputs between themselves and the effect of the structural effect of the model that may depend on several parameters and also have some kind of dependence. So huge debate, like since a decade or so, with tons of different ways to do something. Nothing that is clearly that people say, yeah, that's the way, and now we do this. So open question. Yeah?
Just curious, is it implemented here product composition of two PCEs? Maybe
No.
division of two PCEs?
No.
You do not need it, yes? For example, composition of two functions. I have PCE of exponente, PCE of cosinus, and I want exponent of cosinus.
No, no, that we don't have, no. Still a lot of things that we could put. No. Yeah?
It's difficult to phrase the question. So in a deterministic world, right, I've heard of symbolic regression, which is in a deterministic world, you just have an input-output map, and you try to learn essentially an analytical expression for your solution operator, right? So we have, for example, this beam case, and we know this solution, right? And now we say we have numerics for that, use this kind of polynomial fitting, that's what they are doing there in the same way, to really just get a deterministic function. But the similarity for me is that they also use a basis, which can be polynomial, or even Lagrange, whatever you want, in order to get this mapping.
That's exactly the same. I mean,
exactly the same, right?
everything that I mentioned here, I put this under uncertainty quantification because I use it in post-process to say something about the statistics of something. But you could completely forget any probabilistic thing and say, I have this model, I have data points, and I want to feed a function and do something. And that's it. So actually, we also did this at some point. That's where we started to really merge or link with standard machine learning. We applied this from pure data. If you remember the very first table where I said, well, we have a model, we sample it, we get an experimental design, whereas machine learning starts from already the big data. We really took a number of such examples where we start from the data, which has all kinds of problems because it has fancy distribution, it has dependence, sometimes it has categorical variables, all kinds of things that I did not mention here. And again, PC expansion, sparse PC expansion is incredibly good. So we have already 2 papers on this and a recent work where we did a comprehensive benchmark, and ourselves, we know how it works and we are amazed how it can work on non-structured data that does not at all come any physical model. It comes from, you know, standard tabular data. Okay, it's not for, we don't do LLM with PC expansion or image pattern recognition. I mean, it's for tabular data, but for sure, tabular data in a reasonable dimension, not 1 million, but maybe up to 100 or few hundred, and with not so much data, that is the best way to do, in my opinion. Yep.
Just a general question. You mentioned before the similarity to reduced order models, and now we don't have time to talk about GPs, I guess.
It's up to you. I mean, I have time. We can have a short break, and then I do 40 minutes, 30 minutes. It's up to you. I mean, I'm here, so.
But like maybe quickly, like when you sort PC into the big picture,
yeah.
Where does it fit related to GPs and other reduced order models?
Okay, maybe I can go through the GP presentation, avoiding any math, which was maybe a part of it. Like half of it, and go to what is really useful, okay? So you remember you have seen this equation already, okay, where Gaussian process modeling, we assume that the M of x here, we artificially introduce, and this is artificial, it's not related to the uncertainty I've mentioned before. Just this deterministic function, we assume it's a realization of a particular Gaussian process. Okay, so it's one curve out of infinite number of realization curves, let's say, that is parameterized with possibly a zero mean or a constant mean, or a mean that is a sum of linear combination of non-functions, let's say linear part here. And that is really the Gaussian process, which once you normalize here, it's a zero mean, you need variance, and so it's completely defined by a correlation function, okay? So these are the ingredients. So the degrees of freedom, in a sense, are what you put here. This is called the trend, how many terms, and then you would have to fit that variance of the thing, and then the properties of the Gaussian the standardized Gaussian process boils down to the autocorrelation function, okay? So there could be tons of autocorrelation functions. Typically, so an autocorrelation function usually is equal to 1 in 0 and then decreases this way, okay? So it could be a Gaussian, it could be an exponential, it can be, and that's what we use in more and more people, not just us, people use. It's this kind of funny function here that gives you the correlation between 2 points, because it has 2 parameters. One is that what you find in any of the other functions is the length scale, or the correlation length, which tells you if you have 2 points at the distance L, if basically the model evaluated at these 2 points would be very similar or completely independent. So that's the role of the scale parameter. And that family has a second parameter, which is new, which influences the regularity. So if you have a model, underlying computational model, that is very smooth in terms of x, like infinitely differentiable, let's say, then you could use a Gaussian correlation function or a very large nu here. In contrast, if you have something that is really rough, so like maybe continuous but not differentiable, or C1, but that's it, and then it's not more regular, then you can choose properly the parameters. So it's an a priori choice that you can do. I don't want to get into the details. So the philosophy of Gaussian process fitting now is the following. Again, we start from an experimental design, and we have this prior modeling that says my true model is somehow one curve out of an infinite number of terms that have a certain structure which is defined, and I know a few points. Okay, the few points I know is that for a selected xi's, I have the true value that I have computed in my experimental design, and I would like my Gaussian process to fit this. So because we put this Gaussian world around it, what we basically do is we compute the conditional Gaussian process. So what does it mean? It means now if I take a new point, which later I would like to do prediction with my surrogate, in that point, a priori, because of the prior definition, I have a Gaussian variable defined by what I defined before, the trend and the correlation function. But if I want to take into account my knowledge, which is in other points I know the true value, I will do the conditional distribution of that thing, conditioned on the fact that in this point I have y equal 1, in that point y equal 22, and so on. And as everything is Gaussian, all this conditional thing is everything analytical. So if I skip the math, basically, basically that's an application of something. If you did any probability course, you have seen this. If you have a Gaussian vector with two parts, you can condition one part on the other, and then you get the conditional mean value or conditional covariance. That's application of this, and it ends up with this equation, which we will use as a surrogate, which says if you give me a new x, I will evaluate this equation where you see that I have here now what is called the trend. So if I were to use, let's say, PC expansion with linear terms, that would be exactly that part here. Okay, I would have a set of linear combination terms. But with the Gaussian process thing, which introduces correlation in the Gaussian thing, you have another term here which, well, brings a number of interesting things. Those coefficients here that were unknown, they look like a least square problem. So it's almost like before. If R was the identity and F was my A matrix of before, that's exactly the same. R is not the identity because of the autocorrelation of the process, but otherwise it's just a generalized least square, let's say, that takes into account the autocorrelation that I artificially introduced, and that makes the thing powerful. And one of the things that you get out of it is that if I had a few points and I put a linear regression in between, or degree 1 PC expansion, that's the same, of course it will not be interpolating. Because of this here and because I use the conditional distribution, these things become an interpolator. So you can prove that if I put one of the xi's that was used into this equation, you get the exact y that was the one from the model. First, very nice thing. Second nice thing is you don't just get a predictor, so a surrogate, but you get in each point the accuracy, the self-accuracy of the surrogate, which we don't have for PC expansion. For PC expansion, we have a global measure of the error overall on your input domain. Here, in each point where you predict something, you say, okay, the prediction is this value, but it's Gaussian with this variance, so plus minus something if you want. Again, with analytical expression for the variance. The fact that it is interpolating means also that in the points of the experimental design, this variance boils down to 0 because you perfectly predict with the Gaussian process what you have. It's perfectly interpolating. And when you're further away from data points, so imagine you have data points, you're perfectly interpolating. When you're far away in between, you have more error. And that is what gets out of it. So I comment only the figures and not the equations. That's exactly what I mentioned. This would be a 1D function here. The true function will be, yeah, maybe I can make it bigger. Yeah, the true function is the blue line. Suppose that so that would be my model, m of x, single x. Suppose that I compute m of x just 5 times with 5 points, the yellow points, 6 points. Obviously, it's not space filling. You see that you have 3 points here, nothing here, so it's very bad way, but it's to illustrate the purpose. If I fit a Gaussian process, I will get this curve, the dashed curve that you see interpolates the yellow points, that is close to the yellow points, very close to the true curve, and far away from the yellow points, completely off. But on top of this, in each x here where I evaluate this function, I also evaluate a variance, which allows me to give this bandwidth here. The variance is basically, let's say, this distance between the dash curve and the boundary. And it's supposed to be symmetrical here. And so you see that at the yellow points, 0 bandwidth, because we are perfectly predicting. And far away, here or here, we have a very big uncertainty. So here it's not too bad because the model, in fact, it was not too bad. Here it's completely wrong. Okay? So now we can enjoy these properties of Gaussian processes to do a lot of things. Estimation of the parameters, all this is the machinery. So again, if you're interested, you can read this or other books in details. If you just want to use it from this, let's say, overview I give you, you go to our software, you put your data, click the button, and you get it. Because everything is automatized, okay? So you don't need, it's better to know what's behind, but you don't need to spend months in understanding Kriging equations before doing anything. Now, why it's better, and this comes back after a long digression to your question. When do we use Kriging versus polynomial chaos? So, in general, if the point is to get a surrogate on a domain, there is no answer. Depending on the problem, the best Kriging model you can get or the best sparse PC you can get will be more accurate. Again, there is no reason not to test the two. And so that's where there is no added value from the theory in what I say, but a huge added value from the practice. Once you have spent a week to compute 200 points, very like overloading the computers of the whole institute, with these 200 points, you should test all the possible sparse PC, all the possible Kriging, neural networks, everything, because that fitting is nothing compared to the week you just spent. So once you have the data, you should do this. Why people don't do this? Because people usually know one technique and one package that has this technique. So if you do Gaussian processes, maybe not you, but your colleagues, Professor Kowalski and our group, they do Gaussian process because they are based on some R packages that are very well known and good for Gaussian processes, and that's it. I'm sure there are many problems we would be much better, but it's just they don't use PC, that's it. So one of also the goal of our tools is that we are not advocating any of those. We take whatever works. So it's really agnostic. You give me data, I return you the best surrogate I can do with your data. That's it. But still, there are cases where there are features of Kriging that are interested is this local error. Because then we can do something called active learning. So yeah, we don't care this. So if I look at the width of this blue area here, that is directly related to the variance of the fitted model. Here I plotted this variance. So again, you see it's exactly 0 at my training points. It goes down to 0, and far away, it's peaking. So now I started with 6 points. If I ask you, okay, I can afford one more run, 7th run, which value between 0 and 15 do you choose? Well, you would choose the value where you have the largest uncertainty in what you predicted. So you will just maximize the variance, put a point there, get the true value, again, 1 day of calculation maybe, and then with 7 points, you refit the Gaussian process 5 seconds. Okay? And then this variance error, because you have now a better prediction, overall will decrease. So you can do this in a dynamic way or active learning way, and this looks like this. At each step, you find out the red point is what maximizes the bandwidth of the previous step. You put a point there, you refit, and here after like maybe 20 points in total, in fact, way before you have really an excellent prediction. Okay, so that's the principle of active learning. We can do no, it's not active. We can do enrichment also for polynomial chaos expansion, but not in this. I mean, if we want to do this, we need to get a local error. You remember here, the local error in each point predicted is built in, and that's why it's very nice. For polynomial chaos, you get a mean square error, but no local error. But there's a way, again, to emulate this. This is a very generic technique that is called bootstrapping in statistics, which is the following. If I have like 50 points in my experimental design, I fit my best possible PC. And then for that X, I predict something. No error. Now, out of those 50 points, I will resample, so take 50 points from the 50 points I have, possibly with repetition. So in practice, you will not have the exact same 50 points, still 50, but different ones, because some may be sampled several times, some may not be there. So from this, you get a different PCE, and at that prediction point, now a different value. And this resampling and updating is, again, extremely fast. So very easily, you can get 100 bootstrap things. And so instead of one PC prediction, 100 prediction, and then a variance. And then you come back to this. It's not built in, but it's feasible. Okay? And you can do also something which is, well, really nice to do. And I think only our software package does this because it combines PC expansion and kriging, and not so many groups do this. And the idea is very simple. As a kriging model is defined by a process and some kind of trend, where, again, the tradition in statistics is to put 0 or a constant. That would be Gaussian process. The tradition in kriging, that is the engineering version, would be to put a linear trend. Why not to put a polynomial fancy thing? So that's what we did a few years ago. And not getting into the details, basically, we used the data as if we were fitting a sparse polynomial chaos up to the point of finding the basis. And then, okay, we can get the coefficients, but we just keep the basis, and then we put the basis here. And then we consider, okay, that's our basis. I finally find out of nowhere that I should take x plus x1 plus x2 square, I mean, x1, x2 square, x1, x2, or whatever else. And this should be the right trend terms. And then we fit with standard techniques the Gaussian process. When we do this, usually we outperform any of the two. If we have little data, you see a difference. If you have, let's say, enough data, the difference is tiny, and as it's more costly, it's not necessarily always worth it. But for sure, it's a kind of a combination, the optimal combination of the two. And again, intuitively, not getting into the equations, PC is very good to get the overall form. I mean, polynomials are global polynomials. They are not local. The kriging correlation is good at fitting locally what's going on. So basically, PC kriging, you have the polynomials that give you the overall shape of your model output as function of the input. And if locally you have fancy things, the Gaussian process term will fit it, and you get something that is the best of the two. Yeah. Yeah, so yeah, maybe that ends up with the link between Gaussian processes and, again, this active learning process that at least I presented. It's basically the state-of-the-art way to solve problems of this kind, where you have some output quantity, it's called G here, and you want to compute the probability that that quantity is smaller or bigger than a threshold, and it's a rare event. So that probability is usually a very small number. So to compute this, to compute a probability in general of this kind, basically you can do a big Monte Carlo. But again, if the probability is very small, you're in the corner of the model, you need millions of terms. Okay, maybe still feasible. So you do a PC expansion everywhere, and then you sample 1,000,000 times, and you will get it. The problem is that the PC expansion, or the kriging in general, it will be good overall, but you need it not to be good overall. You need it to be good in the corner with the extreme value. So the active learning things that you have seen before, we can adapt it to this kind of problem so that you start with a very inaccurate surrogate, but the new points you add, they are not now related to the bandwidth of the variance. There's more advanced criteria that makes the surrogate very good in the corner of the the event of interest. Okay? And that is called active learning for reliability, or there are different names. But again, this is the state-of-the-art way of computing small probabilities of failure. Yeah. Thank you very much.